All right, good morning. I'm just going to introduce myself. My name is Ziad Mahfoud. I'm an associate professor of biostatistics. I used to actually be here at the Faculty of Health Sciences. And then 7 years ago, I moved. Now I'm actually at Weill Cornell Medicine in Qatar. I teach Epi and Bio. I teach advanced and introductory courses in biostatistics. And I do a lot of research, especially tobacco use, mental health among kids, and health of pregnant women. So I've been teaching this now for almost 13 years. And we shifted the course into modules of like four lectures during weekends. So that's basically what we're going to come. This is our first weekend. We're going to have the second one, I think, in 6-7 October, and then 20-21, and then the last one will be 3-4. Now, the material is in the syllabus, but I'll go quickly over it. Today, we're going to finish phase 1 and phase 2 trials. And I'm going to start phase 3 a little bit, although I did not put the lecture notes on this, but it's more definitions, so there's not really anything of big material. Then next time we're going to spend all of it on phase 3. I'm going to show you how to actually input statistics in the design of the study, and actually how to formulate a plan of analysis and the simple analysis and what can go wrong. And then we're going to move to special designs. We're going to do crossover designs where actually the patient takes 2 drugs, A and B, with a washout period between them. And then the second one will be factorial designs where actually patient takes a couple of drugs together, 2 or 3 together versus 1. So I want to see a combination of drugs versus 1. And then I'm going to do cluster randomized trials where actually you randomize clusters of people, for example, classes or clinics, instead of randomizing patients. So the whole clinic will take the same medication instead of one person at a time. It's something actually that has been going and getting more attention, cluster randomized trials. And now softwares are actually at ease in working with these trials. And finally, I'm going to also touch on non-inferiority trials and adaptive trials in clinical trials. These are things that I'm seeing more than before. I do a lot of clinical trials, as much as actually we see in the region. So I've designed a few of them in Qatar. I've actually worked on a lot of them here. I'm still working on a few of them here. And I'll tell you my experience with this in the region, what kind of designs we used, and what assumptions we assumed, and what things might go wrong, and so on. So I'm going to start. Yesterday, Dr. Flyhan talked about 4 phases of clinical trial: phase 1, 2, 3, and 4. So phase 1, it's actually the first time you start testing these new medications on humans. So it's first in human. It's after actually animal research. And really here we're trying to study the pharmacology and the toxicology of the drugs. So we're trying actually to find what we call the maximum tolerable dose, or the maximum tolerated dose, MTD. Okay, and this is usually defined as the dose at which people can receive without experiencing severe side effects, or what people call in the literature dose limiting toxicity, DLT. Now, the issue with this is sometimes this can be done on actually healthy subjects. Sorry about that. And in few cases, actually, we work with terminally ill patients because that could be their last resort. Now, how do we do this? I mean, what is a dose-limiting toxicity? So what do you think is a dose-limiting toxicity? What is something that you feel is a severe side effect that? Death. Okay. It could be simpler than that. I mean, sometimes bleeding, unstoppable bleeding or something like this. So it depends on, actually it will depend on what is the disease that this medication is intended to. And I think there is some kind of ranking. I'm not an MD, but there is actually a ranking for the severity of side effects depending on the disease. I forgot the names of them, but each one has a ranking like grade 3, 4, grade 5. So there are grade 1, 2, 3, 4, 5. So when sometimes I do analysis of these toxicities, we actually grade them according to specifics. The physicians will grade them, and we actually will count the percentage of patient will get grade 1, grade 2. Usually these are the very minimal, like headaches and things like this. And then grade 3, more serious, grade 4, and grade 5. So you need to look at that and so on. So for example, of a severe side effects are grade 3 or greater hematological toxicities and so on. Now, how do we find those? So basically, you need to start with a very small dose. And then if you give it to some patients or some actually healthy people, if nothing happens, you escalate the dose. Now, one of these escalation sequences is actually a mathematical series. It's called the Fibonacci sequence. So basically, you start with the first dose, and everything is fine. So the second dose is doubled, so 2 times the first dose. Again, you give it to some of the patient, everything is fine. Now the third dose is actually you multiply, you don't double the second dose, you multiply by 1.67. Okay, so it's a 67% increase in the dose. The first escalation was double the dose. The second escalation was 67% of the current dose. If everything is fine, then 50% escalation, then 40%, and so on. Now, why do you think we don't do every time double the dose, get faster, do things faster? Why do we actually we start very fast, doubling the dose, and then we start actually, no, let's not double the dose the next time. We'll do 67% and then 50%. This is one of these examples. You could miss the right dose, but once you start actually at the bigger doses here, when you double it, what might happen? Severe. You might actually kill some people. I mean, once the dose start getting bigger and bigger, and then suppose somebody you're giving them 4 milligrams of certain medication, then you're going to double it to 8 milligrams. Now at that time, it becomes dangerous to double. So you're getting closer. We know that we are getting closer to the maximum tolerated dose, and that's why at the later stages we want actually to increase the doses very, very minimally, so that we don't. So that's actually, so as I said, that's one of the examples that people use. Now this is called design A. So this is a flow chart. You start actually at the beginning with 3 patients at the initial dose number 1. Now, if you observe no dose-limiting toxicity, on the far left here, if you don't observe any dose-limiting toxicity among these 3 patients, so you find the results of all the 3. So 0 out of the 3 has dose-limiting toxicity. You test 3 patients at the next higher dose, so you go back up. It's a loop. Up. And then you keep doing this. If you're not observing any toxicity, you keep going up to the next dose according to the sequence I just showed you. Second dose is doubled, third dose 67% increase, and so on. If you see only 1 out of 3, so a third, 33% has dose-limiting toxicity, then you put 3 more at the same dose. So now we have 6 at the same dose. Once you have 6 taking the same dose, you have to make a decision. Okay? Now, if these 6, you have still 1 out of 6, then you can go up. If more than 1 out of 6 has dose-limiting toxicity, you stop the trial. Now, what you can see here is that we're only stopping the trial for actually for high toxicity. You're going to see in the future sometimes, especially in phase 2, we can stop the trials in 2 ways. There's 2 different ways to stop the trials. But let's let's not jump. So I repeat this. So you start with 3, 0 toxicity, you increase. More than 1 toxicity, again, you stop the trial. And usually, once you stop the trial, the earlier dose that you used is the MTD. Remember, we're stopping the trial because we think that the current dose is toxic. So the previous one would be the MTD. All right. Now, usually, I mean, at the first time, you're not going to stop it at the first dose. Let me give you an example. What's dose number 1? Dose number 1 is used as 10% of the dose or 10 or 20% of the dose that used with mice and that killed 10% of the mice. So the dose that killed 10% of the mice in the animal study, you take also 1/10 of that, and that's the dose you start on the human. Of course, adjusted for the weight and so on. But that's how small we start. Okay? So it's highly unlikely with the first dose, it's highly unlikely you go to stop the trial on the first dose. Okay? But in case that's happened, then you have to stop, and then you start at a much higher dose than you needed. However, again, so once you get 6 at the same dose, either you increase or you're gonna stop. So if you keep increasing, that's fine, and then at the end you're gonna stop. So once you stop, please remember that the MTD is the dose that is prior to the dose that you stopped at. So this is what some people call 3 + 3. It's called design A. I'll show you another design. Any question about this one? All right. Now this is called design D. So this is a different stopping rule. So I'm telling you there's a lot of different stopping rules. So the stopping rule on the first one was 6. If more than 1/6, you stop. If less than 1/6, you actually escalate the drug. You made more. Now here, again, you start the same thing. Start with 3 patients with this is the same flow chart. You start with a 3 patient. If 0 out of the 3 had dose-limiting toxicity, you increase the dose. If 1 out of the 3 has a dose-limiting toxicity, you put 3 more at the same dose. So now we have 6. If the percentage of dose-limiting toxicity is less than 1/3, which basically is still 1 out of 6, by the way, then actually stop the trial, and the current dose is the MTD. If more than 1/3 out of those 6, more than or equal to 1/3 out of those 6 tested at the same dose, then stop the trial, and basically the prior dose is the dose-limiting toxicity. So here you can see the stopping rule is slightly different than before. And of course, if more than 1/3 from the beginning, 1/3 of the patient has a dose-limiting toxicity, you stop the trial early, and the lower dose would be. So here you can go back, and the only main difference also here is that once you do 1/3, you can test 3, go back. So in the previous one, if we have 1/3, we stop. Here we can de-escalate. In the previous one, we could not de-escalate. We are actually only escalating. Here, we start 0, we escalate 1/3, we put 3 at the same dose. We have to make a decision directly here. And then if it's more than 1/3 DLT, then basically we can de-escalate, and then we have. All right. Yeah, so one, all right, so let me take an example. I'll take an example and I'll go through it, and we can take some scenarios. If let's start with 3 patients. So I'm gonna start at the beginning. This is dose number 1. I have n equal to 3, dose number 1, n equal to 3. Suppose we observed 0 toxicity, 0 out of the 3 DLT. So no DLT. So basically, what should be my escalate? So now I have D2, I put n equal to 3 on D2. All right, so we start with a cohort of 3 at dose 1, 0 of them had any dose-limiting toxicity. Then we take another 3 patients or people at actually dose 2. Suppose we observed here 1 out of the 3 has or experienced DLT. So 1/3. So according to this, if we have 1/3 experienced DLT, then we should put 3 at the same dose. So now, I have still n equal to 3, another 3 patients at D2. Once we have 6 at the same dose, we have to make a decision. Okay? So you know by that fact, when you did this, you had to make a decision, and the decision is either, depending on the next cohort, is either to stop the trial and the current dose is the MTD, or to stop the trial and D1 is the MTD. So if I go back here, from the first cohort, we had 1/3, one of the patient had DLT. Let's take 2 scenarios. If we had 0 DLT in the second cohort, then the total would be 1 out of 3 first and 0, so 1 out of 6. Okay? If you have 1 out of 6, then basically you're going to stop that. We know we're going to stop the trial, but the probability of DLT is actually lower than 1/3. 1 out of 6 is less than 1/3. So we stop the trial, and D2 will be our MTD. So this actually indicates, so if we have total 1 out of 6 from these 2 cohorts at D2, then actually D2 is the MTD. So that's the first scenario. Yes?
This stage that we have less than 1 or 6, so why don't we go for escalation?
Sorry, at what stage?
This.
Here?
Yeah. Still we have less than 1, so we will not go further for escalating?
No. The idea with this is that once you get 6 patients treated at the same, then you need to actually to stop.
Whether it is...
Yeah. Because you already saw 1 here, and then you're just confirming. It's kind of a confirmation. Because this is at the first stage, when you had the first cohort, you had 1 out of 3. Okay? To go to another 3, you're just trying to see if it's not toxic more. So it's already, in your opinion, 1 out of 3 is toxicity. So now, if it stayed 1 out of 6, you say, I'm happy with this one. If it becomes 2 out of 6, you say, no, let me de-escalate. So this is the second scenario. So if in the first cohort we have 1 out of 3, and the second cohort we had none, so total is 1 out of 6, then we're fine, and the current is the MTD. The current dose is the MTD. If in the second cohort we had 1, 2, or 3, it doesn't matter if we had any toxicity in the second cohort. Because if we had 1 out of 3 in the second cohort, and we have 1 out of 3 in the first cohort, then we had actually 2 out of 6. If we have 2 here in the second cohort and 1 in the first cohort, we had 3 out of 6. And if we have 3 in the second cohort, 3 DLTs, and 1 DLT from the first cohort, we had 4 out of 6. So all of those 2, 6, 3, 6, 4, 6, all of them are equal to 1/3 or actually bigger. So in other words, if the second cohort had 0 DLT, the current is the MTD. If it had any other DLT 1, 2, 3, then the prior dose is the MTD, which in this case is dose 1, for example. Now I'm saying this, you think it's dose 1, but really usually in most of those trials, we go approximately 10 doses. So it's highly unlikely to stop at dose 1, okay? So you go 6, 7, 8, depends on how much toxicity. Remember, we're starting with very, very minimal. And there is an ethical issue also with starting with a very minimal dose. And it has no therapeutic anything, and you're delaying if you want to get to the MTD, the accurate MTD. So that's why we have to have alternatives where we might want to start with a bigger dose slightly, or we might want to rush very quickly to find the MTD. All right? Any question about this? So these are 2 types. As I said, design A, which is the prior, so this is slide number 3, slide number 3. You start with 3 patients. If 0 toxicity, you add another 3 on the next dose, so you escalate. If 0 toxicity, you escalate. If 1 out of 3 had toxicity, you put now 3 at the next at the next higher level, and so on. And if it's more than 1/3, you stop the trial. And basically, once you get here 6, you can either, if it's stage 1 out of 6, you go up, increase, and if it's more than 1/6, you stop the trial. And the second one we just explained to you. Yes? This is, I mean, it depends on, I'm going to show you a couple of other ones. It depends, sometimes at the end I'm going to show you a comparison of all these designs. So it depends how fast you want to get the MTD, how many patients you want to use overall in the study, and what's the expected stopping early. Yani, if you can stop early, you want to say, I want to use this design because I might get faster, stop early. So there is a paper which I actually, on the Moodle, I put 3 papers for you. These papers are not really, some of them are very technical, so they're not required for you to read, but these are where some of that information comes from, is how to compare. One of them is how to compare different designs, and one of them on another design that's called CRM. I'll explain it in a second. Now, yes?
You put on the slide cancer research. It's only for cancer research, or?
No, usually not necessarily. No, usually it's healthy patients, healthy people.
I mean the drug.
No, it could be any type of drugs. All drugs has to go through this. I mean, you want to look at the pharmacology of the drug, and then also, but this is basically, you want also to look at the toxicology, find that dose. No, any drug. All right. So in order to actually expedite finding the MTD faster, people came up with a couple of other designs. This is called the 2-stage design. So at stage 1, instead of treating 3 patients at a time, treat 1 subject at a time. If no toxicity is experienced, then increase to the next dose. When a toxicity is observed, use the next lower dose and go to stage 2. Okay? So basically here, if you don't find any toxicity, you increase, but with 1 patient, instead of waiting for 3, just 1 and 1 at a time, so you go faster. Now at stage 2, whether at 1 level you'll find a toxicity. Once you find a toxicity, you go to stage 2, and here you use either design A or design B. Okay? So this is, it gets things faster. Now, another one, so instead of the 2-stage design, this is called the continual reassessment method, CRM method. Now, the CRM method is based on using data from the first cohort to inform before doing the second cohort. So I have 3 patients. I can actually have data on these patients. Why don't I use that data to inform me whether actually the next dose should be escalated twice or 3 times maybe versus actually de-escalation? So let me go quickly through this. Again, you have an article I put on Moodle that says understanding CRM. It's just very untechnical, this one, just to understand what's CRM. So this is first suggested in 1990 by Quickly. And there's so many modified CRMs versions, and I put here for you a lot of references with just the author name and actually the year. So what's the basic CRM? You assume an increasing dose toxicity curve. So you start, and this is true. I mean, the more you give dose, you expect toxicity to go up. So I'll do a graph here, a simple graph. So on the x-axis, I'm going to put the dose. So on the x-axis here is the dose. And on the y-axis, percent toxicity. So a percent of people, if you want, who experience DLT. And we're going to assume an increasing function. You can assume an increasing function. A lot of people use the logit model. I don't know if you've seen the logit model. Some of you might not. But the logit model is an increasing function that goes up like that. It's like an S. All right? So it's an increasing function. And which basically it's log dose over 1 minus dose. That's basically what the logit. So if the dose is X, then Y log x over 1 minus x. So something like this. All right. And of course, the minimum toxicity at the y-axis should be 0, and the highest toxicity, percent toxicity, should be 1. Yani everybody died, or everybody experienced the DLT at the high, at the top. All right. So, and you assume percent toxicity at the beginning. You say, all right, I'm going to define the MTD where 20% of the patients are going to assume toxicity. In our experience, if you go back to our design A and B, we used 1/3 as our, if you want, as our cutoff for toxicity. You can use anything you want. Some people use one, you're going to see a picture now is 40%. So let's use anything. So I put a percentage, a horizontal curve, let's say at 30%. So basically I'm going backwards. I'm saying where this curve, where this log pi over 1 minus pi crosses with the horizontal line of 30%, that actually is my MTD. So the MTD is defined by the researcher as the value of the dose at which 30% of the patient experience dose-limiting toxicity. Now, again, there are assumptions here. You are assuming a curve, and you are assuming some kind of, you know it's increasing, all of us know increasing, but there could be different types of increasing curve. Now, what we do is after we get this first patient cohort that we use, okay, so we start with the curve, you start with the cohort, and after you get the initial estimates of the MTD from the curve, the outcome from this cohort of this patient is used to update the dose. So I looked at, let's say I took a dose of 3 people, and 2 of them had toxicity already. So that's 60%. So I know, for example, if the dose, I suppose I suspected the dose here is 5 milligrams. But when I started with actually 3 milligrams, I had 60% toxicity or 67% toxicity. Then what I do is I update the graph. And I say, according to my cohort before, the graph actually, toxicity is much higher than usual. So in this case, for example, you might have a picture that starts, the curve might be either above the original curve or below the original curve. So if the curve is below the original curve, we'll take 2 scenarios. And the curve is above the curve. So basically, we're updating this curve. And we're still looking at 30% horizontally. And according to this new curve that is higher than the older curve, now the MTD should be lower than what it's supposed to be from the first estimate. The MTD goes down. And if I observed fewer people from the first cohort who observed MTD, then my updated curve is going to be below the original curve. And then when I cut 30% horizontally, then the MTD now definition is going to be above the original one. So basically, I'm not gonna test you on this. I'm just gonna explain. I'm explaining this to you because this is a concept. This is not gonna be a question. But what I want you to know about the CRM is 3 things. I want you to know that basically we assume this curve, and according to this curve, we start with the initial estimate of the MTD, which is at 30%, at a 40%. We start initial estimate. We get the data from the first cohort, and according to this data, we update our curve. And by updating this curve, the next MTD could be higher from the current, or then our next estimate of the MTD could be higher, and then, or it could be lower. This is the idea. Now, the nice thing about this is that you could jump like 5 doses at one time or 3 doses. If, for example, in the first cohort of 3 or 6 patients, you got 0 and you updated the curve, and the next time you try to check your estimate of the MTD, it could be 2 doses instead of 1 dose escalation. It could be 2 doses escalation, or it could be 2 doses de-escalation. So basically, this is the advantage of this. Now, when do we stop? So the idea is that when do we stop? So we stop, there's different, as I said, there's a lot of versions of this. One of them is when you use a maximum sample size, let's say 50 patients. After 50 patients, you stop. Some people they say no. Once the MTD, and once you start updating this over and over, at the end, by updating, you should be getting close to the true MTD. So at the end, after a few iterations, your MTD estimate is not going to be changing anymore. So once it's less than 10%, you say I'm going to stop and I'm going to use that as my new MTD. The final curve is going to be used to estimate the MTD. So the curves are getting closer to closer after several iterations. They are not changing that much. When the change is less than 10% in your estimate of the MTD, you stop. Okay, so this is here. So note that, on slide number 7, you can see that the first say, note that CRM allows escalation and de-escalation of more than one level at each step, which might help in speeding up the process. But we talked about escalating too much is too risky also. Like we said in the first thing, I don't want to escalate too much. So some people modified this. So that's why the original CRM might allow you to escalate 2-3 doses at a time. And you are worried as an MD that this might actually cause some severe side effects. A modified CRM, there's a different version. A modified CRM starts with a 3+3 standard dose escalating procedure until first DLT is observed, preventing starting at a high dose in CRM that uses just a guess of what the dose toxicity curve. So that's another version. So a modified CRM start 3+3, like design A or B. And basically, once you find an estimate of the MTD, use it, and then start with this. The other modification that is important is that escalating is now restricted to one level. So some people also said, let's do escalation. Even if the curve is going up, we're only going to escalate actually one dose. Okay, so sometimes on the x-axis of these curves that I talked about, they call them dose 1, dose 2, dose 3, dose 4, instead of like percentage in milligram or number in milligrams. So they allow you only to escalate one level, but de-escalation can be actually large. So if you are at a higher level, you can de-escalate faster, again, to protect the patients. And the trial stops when an a priori fixed sample size is reached. That's one of them. Some people suggest when a target dose changed by less than 10% also, as I said, when your estimate of the MTD is not actually changing that much. Or you reach a certain precision of the DLT curve. So the curve is it's not changing that much, your curve. So next slide, you see this is actually, these are the graph that I showed you here. On the x-axis, the dose level, and they call them 1, 2, 3, 4, 5. Although it's continuous, we need to think about it, dose level is continuous, but at least they put some numbers. Dose 1, dose 2, 3, 4. And then you, on the y-axis, you have probability of toxicity or the percentage of patient got toxicity. You start with the solid line is your first estimate of the dose toxicity curve. And this is actually what we call a logit curve. And again, they use the probability. You can see there's a horizontal line at the 0.40% probability of toxicity. So according to this, the first estimate of the MTD, if I go down here, it should be dose number 4, something around dose number 4. And you can see there are 3 dotted curves, and these 3 dotted curves are possible changes depending on what from the first cohort you get information. So if the curve is if the new curve, the dotted curve, is we use the first one here, it's below the original curve, then you can see that we are escalating. So the next dose will be almost dose number 5. If you use any of these 2 curves that are above the original curve, then at 40%, you're hitting something actually before the dose number 4. So you are de-escalating either by 1 or de-escalating by 2. So this allows you this. So the concept, these are the concepts. Again, you can see that there are a lot of assumptions here, okay? And the main assumption really is starting with what is the curve we're going to use, and is this true or not? But it has, so this is, it has proven some actually benefit in finding MTDs, and people are using it. A lot of people still use the original ones, design A and B. Very simple, very easy for people to understand. This might be complicated and a lot of assumptions. So let me, slide number 9, we're talking about ethical issues in phase 1 trials. So the first one is obtaining MTD slowly, especially in designs A and B. Okay, basically you're putting 3 people at a time, 3 people at a time at starting. Remember, we're starting with very low doses. So basically, especially for example, if these actually are patients, not healthy participant, volunteer. If these are patients, you're giving them suboptimal doses, and there's no actually clinical value or therapeutic value for those. So you're giving them ineffective treatments. Although we are not actually treating them, we're trying to find the dose, but when you start working with terminally cancer patient, then basically you have to think about these issues. Now, the second big issue is exposing subject to doses above the MTD. With this escalating, we might actually at one time expose subjects at an MTD that is at a dose that is much higher than MTD. And that might cause actually severe outcomes, which basically it might be death. Okay, so that's why some people, depending on what disease you're working with, some people might want to start slowly, and some people say, no, we're doing actually a drug for I don't know, allergic reaction, so it's fine. The maximum is you can treat. If something happens, you can treat them easily. Okay, so it depends on this. Now, another issue is subjectivity in deciding on the term of severe outcomes. As I said, I mean, I'm not an expert in this, but in my work, I worked a lot on phase 2, especially phase 2. We actually, the events, the side effects are graded as grade 1, 2, 3, 4, 5. And this is now internationally by like a society of oncology or hematology or something like this. They actually grade them, and you can decide on that. But still, I mean, this has to be well defined. Now, some people think about, there's a problem. Most of these studies have small sample sizes, 20 patients up to 80 patients or 50, 30 patients, of how can we actually make inference? How can we decide on everything based on only 40, 50 patients? And these patients might not be very actually homogeneous, or these might be volunteers who actually might not satisfy the inclusion criteria for the drug when I'm going to use it later on. So there's a lot of issues. You're getting volunteers, so the volunteers might be very heterogeneous, and so there is no criteria that's much well defined. However, in the literature, there's a lot. I mean, if you go to PubMed, put phase 1, you'll see a lot of publication on phase 1 trials. And finally is how to compare phase 1 trial, and that's the third article I put there. And I'm going to show a table from that article, and that table, you have to look at some indicators and decide on those indicators. So in this actually article, they did simulation. They defined an MTD. They said, let's suppose we know the MTD, and let's see which of those methods actually can reach that MTD faster, and how many patients they used, and so on. So they did a simulation. They said, and of course, if you repeat the same study, you're not going to use the same number of patients and so on. So for example, design number A. So they know the MTD, and they said, let's do design number A 50 times. Okay, sometimes you reach the MTD, sometimes they don't reach the MTD. Sometimes you use 50 patients, sometimes you use 60 patients. So they did that. Let's use the second design. Let's use CRM. Let's use two-stage designs. And let's compare these indicators. The first one, which is very important to us, is how close is the average estimated MTD with respect to the true MTD. Why I'm saying the average estimated? Because for design A, they did 50 times. So each time they have MTD. So on average, how good was design number A or design A? The average number of patients used in the trial, again, with design A, sometimes they use 50, sometimes 60. On average, design A, how much they used? Average number of patient cohort used, instead of number of patients, how many cohorts they used, okay? And percentage of patients in the study who experienced a DLT. So the percentage of patients, so sometimes in the first run of design A, nobody experienced DLT. We reached nobody. Could that be true? Nobody experienced DLT in a phase A, in design A.
Then how did we stop?
Exactly. We could not stop. So at least you have to have one or two, actually, to stop. So the percentage of the patients, so maybe we used 50 patients, but at the last stage we had 2 DLT in a cohort of 3, and we stopped at that time. So 2 out of 50. Next time it was, I don't know, 3 out of 70. So, and this is the table that's from the article. On the left, on the left axis, on the left, you have the dose level. So the first column on the left is dose levels, and you have the second column is true probability of toxicity. So you have 5% toxicity, 10%. So this is what they fixed the simulation at, okay? And then you have, for each of the left other columns, you have the standard drug, the standard method, I mean, and you have different CRM. The fourth column is CRM number 1, CRM number 2, 3, 4, 5, modified 2-stage CRM. And the last 2 columns is 2-stage modified Stror, and then 2-stage core. So there's a lot of designs you can see. Let's pick an indicator. So I'm going to pick on one of these indicators, which is average number of patients used. Under the standard drug, it was 16.4 patients. Under the second CRM one is 14.7. You can see, and then it's 15.4 and so on. You can see the numbers are very close to each other. It's not like I have one that used 14 and the other used 500. If I look at the percentage of people observed toxicity among the patient, under the standards, about 20%. Under CRM, 1-stage modified CRM is about 29%. And among the CRM, all of them, you can see it's in the 20s. And then also the last 2, the 2-stage modified Stror and corn, they are all above. So actually, the standard technique gave me the lowest number of percentage of patients who experience DLT. Now, what's important also for me is if I go up, when I look actually, the MTD that was declared, in these studies, what's the percentage of people who experienced DLT, or what's the proportion of patients, at what proportion? For example, in the simulation, if we fix it as 25%, so the MTD is defined as 25%. Now you can see that, again, the standard one gave me a percentage of 30%, close to 25. So the MTD that was used for the standard was at 30%. During a simulation was supposed to be at 25. So you want this to be closest to 25%. So this was 30%. Under CRM1, it was 41%, 42%, CRM3 is 33%, and so on. So again, you can see that design A is doing slightly better than the rest of those. And the last row here is the average number of cohorts. And again, you can see that design A, the standard design is doing better. That's why a lot of people still like the standard design. Although some people are trying to use this, because remember, these are on average. So when you do the simulation so many times, you still see CRM used in this. I personally, if I'm working with this, I did only one time. We use actually the second one, stage design D, not design A, design D, where we actually can escalate and de-escalate. So that's what we used. So anyway, so this is all I want you to know about phase 1. Really, this course is mainly about phase 3. I'm gonna elaborate a little bit more on phase 2, because in oncology, a lot of people do phase 2. And I just actually designed one for AUB-MC, a phase 2, helped on designing one. Actually, looking at the sample size, looking at and I'll actually show it to you what we did. Okay, but phase 2, you start seeing in the region a lot of phase 2, because these are cancer trials. Most of the cancer trials are phase 2, especially when trying new drugs. All right, and so on. So this is basically, so phase 1, as I said, you need to know the basic designs. So if I give you a basic design like design A or design the first, if I go back to the slide number 3, which is design A, and then slide number 4, which is design D. Now the names are taken from the publication that the person Stroher is the guy actually who did these. So these are the names he gave. And there's actually design B and C, but I did not discuss them. If you would like to look at them, I can send you the paper. But these are the easy ones to use. Two-stage is fine. It's very simple. You can understand what's two-stage. And then CRM is the modification. And of course, you need to understand what are the ethical issues with phase 1. And basically, picking a phase 1, I'm not going to give you a table and tell you this, but I'm just showing you which one, because the question was, how do we pick between them? Again, we start going, I mean, standard is doing very well, and some people like some other ones to work with, okay? For example, if I go back to slide number 11, where you have the comparison between all these design for phase 1, you can see, for example, that CRM1 on average uses lower number of patients than actually the standard one. This 14.7 on average number of patients versus 16.4 on the standard. Again, it's not that much, but some people think about these issues, okay? And they like this for more than that. All right, any question on phase 1? All right, so let me start with phase 2, and then we'll take a break after a few, maybe half an hour. So phase 2 is depending on which disease you're working you're working on. It could be just, again, trying to prove that, basically you want to try to prove that this is a promising drug, that there is actually some efficacy, the drug is actually promising to take to phase 3. Because phase 3 is the full-blown study. However, in oncology, why I'm saying this, because in oncology, actually, phase 2 is sometimes called pivotal trials. Remember yesterday, Dr. Fleihan said phase 3 are pivotal trials. Actually, all phase 3 are pivotal trials, because phase 3 are the trials that the FDA requires for approval of drugs, phase 3, not phase 2. However, and that's why a lot of people don't even mention the word pivotal with phase 3. So they refer, when they say it's a pivotal trial, it's actually called a phase 2B, okay, which is actually where you almost proved efficacy. You almost proved efficacy, and sometimes the FDA might give you approval for a drug pending a phase 3 result going on, okay? And so, because this is actually, the patients are at danger, you need to start on something. Now, people also talk about these pivotal trials as a proof of concept. The whole phase 2 issue is that you're proving the concept that this new drug is actually going to work. And sometimes when you read an article of phase 2, you feel it's like a phase 3. There is power, there's sample size, there's randomization, there's everything. The only difference, especially when I'm talking about phase 2B, these pivotal trials, the only difference is that they use what we call surrogate endpoints. Okay. Everybody here knows what a surrogate endpoint. So a surrogate endpoint is basically an outcome that is reached faster, that you can measure easily, quickly, and then it can predict the main outcome. So for example, in oncology, the main outcome is survival, okay? Now, a surrogate endpoint, which some people debate on this, is actually, for example, the shrinkage of the tumor. Okay, the percent is shrink is 50%, 70%, or progression of the disease after surgery and things like this. Now there's debate. There's a lot of articles when they say progression-free survival, time from surgery until the disease comes back, if you want, does not predict actually survival of the patient. Okay, so if some people might progress later and then die quickly, faster, and there's a debate. But there is a lot of these surrogate endpoints that are very strong in predicting the outcome that you're looking for. T cells, for example, for HIV and things like that. So there are some of those. So here in these trials, instead of waiting so long for those, they use these surrogate endpoints. And that's why a lot of people actually, I mean, sometimes I wonder, why did they call, I'm reading an article, it's like, why did they call this phase 2? It looks like a phase 3 trial, but then you look at the outcome is not really the true outcome you want to look for. And so it's a proof of concept. A lot of people talk about proof of concept. So phase 2A, these are pilot studies to evaluate safety and efficacy. So again, if somebody asks you what's the major, what's the objective of phase 2, is basically showing early signs of efficacy. That's the main objective of phase 2, is showing an early signs of efficacy that the drug has a promise. And of course, all the time you have to monitor safety. Okay? In phase 1, it's all about safety. In phase 2, we monitor safety. In phase 3, we monitor safety. And in phase 4, it's long-term safety. So safety is always, it is in all phases. But here, really, the objective is to look at efficacy. Now, in phase 2A, is, again, these are pilot studies to evaluate safety and efficacy. Now, the objective is look at different types of dosing, frequency of dosing, the type of patient, try to look at dose response curve. So if you use 3 times a day with this dose or 2 times with that dose and so on. So there might be selection trials where actually they use different doses and try to see which one would be the best. There could be one-arm studies that have historic controls. So I have actually an already standard drug that's been being used, and I already had patients, so many patients on this, so I don't want to get more patients on this. Now, in general, so historic controls, basically you look at your database, you take patients on the standard drug, you look at how they are doing, and you compare them to the new patient on the new drug. Okay? So what's the problem with historic controls? What do you think is the problem with historic? What's the problem with taking data from a database on old patients, on older, not old patients in a sense, on previous patients I meant, and basically compare them to now patients, new patients are taking the new dose, are taking the new drug. What do you think there's a problem with historic? And this could be in anything, I mean, not necessarily in clinical trials, using historic data as a comparative arm.
The methods used to measure the drug dose or the level in the blood.
The methods.
More sensitive like these days.
So, of course, if there is difference in the methodology of actually evaluating the patients, then that's actually a problem. What other thing could be?
You don't know what's really the patient has got as drug, which can interfere with the status, the health status.
What other drugs they're taking?
Exactly.
It could be in the records. I mean, you can have the medical record, you can look at it and see what they're taking. Now, one main issue is that the standard of care might change. So let's say previously you were giving these patients are doing this, you're following them actually less. Now the new patient, you are following them more. So you are treating them better. The standard of care increased. Now you're requiring them to do extra lab tests and then give them other drugs in order to treat other comorbidities they have. So in that, the comparison is not. So you need to think that the patients are not the same in a sense. Those patients, it could be if it's a short duration of time, nothing changed. And it could be fine to assume that it's homogeneous. But sometimes if you use data from 3-4 years, historic data on patients from 3-4 years, you run into the fact that now healthcare is better. Maybe there was a national, for example, national campaign to fortify milk with vitamin D. And now people are taking vitamin D. I mean, now my patients that come to me are already have better vitamin D levels, and that might affect what we're looking for. Okay? So these are the issues that you want to worry about when you use historic data. Okay? The type of patient, the type of healthcare, and so on. All right. And these kind of phase 2A studies use what we call early surrogate endpoints. So you want quicker results because you want to finalize what's the best dose regime or what's the dose response curve you want to work with. Phase 2B, which is these are the most rigorous demonstration of a medicine's efficacy pivotal trials. Randomized, but not necessarily comparative in a sense that it's not necessarily powered. So sometimes they randomize patient for comparison, but without power analysis. So there's no sample size computation, pure sample size computation. I'm going to show you a few designs that actually they do have sample size computation. They look at what's the alpha level of the study, what's the power of the study, and so on. But sometimes they can just be comparative, just in a sense that it's not powered. So it's randomized, but not powered enough. These use late surrogate endpoints. Some people might say that the late surrogate endpoints, that the surrogate endpoints that take some more time, might be more predictive of the true outcome, not the early ones, okay? And again, there is a lot of controversy. Still, for example, when I go to conferences, you can look at pharma companies actually fighting against each other because one company produced a progression-free survival that her drug are better than the other drug, and the other one showed an overall survival that their drug is better. Now, the overall survival is the one that we want to use, but usually in this cancer trials, a lot of patients leave the studies. So the overall survival at the end of the study is very, in a sense, a little bit biased, okay? So we'll talk, if I have time in this class, which in the previous year we did, at the end I gave also survival analysis, like 4 or 5 hours on survival analysis, so that you can actually, it's something really now I'm seeing a lot in the region, studies on survival analysis, on oncology. So they use late surrogate endpoints, for example, disease recurrence or disease progression in oncology. Now, phase 2A, phase 2B, they could be also one arm, non-randomized. So endpoint is oncology. Actually, the study we just did for AUB, it's a one-arm study. There is no comparison. What we're comparing it to the current drug, but with the current drug is so established that we know, for example, that the percentage of cure, let's say, or the percentage of specific outcome is 30%. It goes by 5% in this country or so we know that. So instead of again bringing more patients on the same drug, the drug is being used right now. We're trying the new drug, and we're saying if it is actually, we want to prove if it's better than 30% or less than 30%. So we use that 30% as our actually alternative and null hypothesis in our alternative analysis. So the endpoint is oncology response rate of the tumor to the intervention, where response could be classified as either complete or partial response. Now, again, in oncology, the response is called complete response, partial response, and no response, or actually getting worse, or stable, and then getting worse progression. So complete response is defined, again, these are well defined in any protocol. That has to be very well defined. These are just examples. Disappearance of all measurable and evaluable tumor lasting for at least 1 month. Survival, time to recurrence of cardiac arrhythmia, for example, in anti-arrhythmia drug trial. Partial response, it could be a 50% or greater shrinkage in the cross product of all measured lesions lasting at least 1 month. There must be no new lesions and no growing lesions. And in the anti-arrhythmia drugs, it could be percentage drop in heart rate, okay? So each study might have its own, and actually in the protocol, they go extensively into how actually going to measure this, and how they're going to measure the tumors, and so on. So you go 3-4 pages of this, and who's going to do that, and so on. But basically, you want to look at this surrogate outcomes. Now, this is the design consideration on slide number 17. You can see the null hypothesis. We started the following, that P is less than or equal to a certain P0. So if our drug is actually worse than a minimal percentage of response, then actually that's not a good drug. So HO represent, if you want, an ineffective drug. H1, if the probability bigger than or equal to a certain specific P1, which that P1 is taken from the literature. So if the current drug has a 30% complete response, for example, and if our drug shows 30% or even higher than that, then that's our H1. So our H1 is that our drug is at least as good or bigger than this. So it's like a non-inferior drug, okay? Now, if HO is true, then the trial should be stopped and the drug ignored, of course, if you have a percentage of complete response or partial response less than a very small number. And if H1 is true, then the drug should continue to phase 3 clinical trial. Okay? Now, a lot of people sometimes think that phase 2 by itself is an end of the drug and the drug should be approved for that. No, no. Still, actually, at phase 2, you will get a P, in some of these studies, you'll get a p-value, but that doesn't mean that the drug should be approved. It's up to the FDA to give you maybe some kind of approval, primary approval until you see the results of this. Even in phase 3 sometimes, in phase 3, again, if you go in details, there are phase 3A and so on. And sometimes after phase 3, you finish most of the patient and you get the results are so strong, you can apply for an early FDA approval and they give you to you and then they want you to update them directly after you finalize the data collection and so on. So that's only if the drug's showing really very good. All right. So going back here, so if H1, our drug is really bigger, our percentage bigger than P1, then we take the drug to phase actually 3. Now, among this HO and H1, so HOP is less than or equal to P0, H1P is bigger than or equal to P1. What do type 1 and type 2 errors represent in the above setting? I remind you what's a type 1 error. I will go over this in actually in phase 3 later on. What's a type 1 error in a study? A type 1 error is when you say that your research hypothesis is true, but in reality it's not true. And you support H1, when you support H1, and then but HO is true. Remember, you don't know that you're doing a type 1 error. Okay? It's just the trial, by luck. I mean, hopefully you want to protect yourself against it. And that's why we use an alpha of 5%. That's why we use the p-value less than 0.05. And that's how we protect ourselves. So we'll talk about this when we go to sample sizes later on. But the type 1 error, when the researcher or the pharma company claims something and afterwards we got proof that it's actually not true. A type 2 error is the opposite, where actually H1 is true, the null hypothesis, your hypothesis, the research hypothesis H1, which is your hypothesis, is true, but you are not able to prove it. Your data did not support that. All right, in terms of this drugs, now we're talking about the new drug. In terms of this drug, what a type 1 error means in this. I know, for example, here a type 1 error is to say P is bigger than or equal to P1, but in reality P is less than or equal to P0. So we're supporting H1, but HO. But in terms of drug, what does it mean? Remember, here we're trying to discover a new drug. So type 1 error means that we're saying our drug is promising and we're moving it to the next stage, but in reality that's not true, which is problematic because what's the next stage is phase 3. And phase 3 where you get thousands of patients to put on the drug. So imagine a type 1 error here is very problematic because it allows you to go to test this new drug on a bigger sample size, and you don't want to do that. And that drug is in reality not that good. However, also a type 2 error is problematic because a type 2 error here is you're missing on a new promising drug. You're saying this new drug is not good, but in reality actually it is good. So it is actually, again, you are missing on that potentially good drug. So that's why there should be also considerations of alpha and beta, which is alpha is the probability of type 1 error, which usually we set at 5% in our studies. And beta is the probability of type 2 error, which usually we set at 10%. Ethically, actually, we are more accepting of missing a drug than actually giving a non-effective drug to a big group of patients. So that's why our type 1 error, alpha as 5%, is always lower than beta, our type 2 error. You can have them both very low, but usually you can see this later on. Some of you might have seen it, is that alpha and beta play a big role in sample size computation. And if you want to decrease type 1 error and type 2 errors, the more you decrease them, the more the sample size goes up and up. And that's why we have to reach a compromise. I mean, otherwise we cannot do any research, okay? So again, we'll see a few of those. All right, one-stage design. So I'll do this one-stage design, then I'll give you a bit of a break. So one-stage design is one group of n subjects are given the intervention. Very simple. X equal the number of successes. So I have n is the total number of patients, and x is the number of succession. And I have a cutoff. R is a cutoff point. We call it a boundary. And R is actually a function of alpha and the sample size, and what's P0 I used in HO, okay? So what P0 I use in HO. And it's very simple. If the number of successes is lower than R, then reject H1. In other words, this drug should not continue to the next step. So if I have my number of successes is below what I expect R, if you want R is the cutoff I want. If it's below that R, then basically I should not proceed to phase 3. So we say reject H1. And we never see in statistics that you took, you never say reject H1. You say reject HO or accept H1. And if the number of successes X is bigger than or equal to R, so you reach that boundary and you exceeded that boundary, then reject HO and take that drug to the next level. Okay? Very simple. You start with a number of patients, you look at the number of successes. Here, number of successes probably is the number of people with complete response or partial response, depending on the outcome that you used. Okay? And if you reach the boundary or you exceeded the boundary, you say, okay, this is a promising drug. And if you did not, you stop and say no. Okay? I'm not going to go to phase 3. And I'll show you, there's a table, I think, if not mistaken. Yes. This is a table taken from this article in Statistics in Medicine. It says sample size tables for exact single stage phase 2 designs. And you can easily use it, and then I'll show you later on different things. So if you look at this table, this is all for a P0 of 0.05. In other words, if 5% of the patient have our response or less, we don't want that drug. P1 could be 10%, the second column, P1 could be, you can see 10%, 15%, 20%, so it goes all the way to 95%. So when you do a study, you need to define P0 and P1. So for example here, if I took P0 is 0.05, which is, you might have other tables for P0 equal 0.10, P0 equal 0.15, and so on. But if P0 equal 0.05 according to this table, and I pick any P1, let's say I pick P1 equal to 0.20, okay? So I'm comparing, so if the drug is 5% or less, has a 5% efficacy or less, I'm going to reject it. If it has 20 or more, I'm going to actually, so I'm use P0 equal 0.05, P1 equal 0.20, and then the next 4 columns is for different alphas and betas. You can see they don't show beta, they say 1 minus beta. 1 minus beta is the power of the study. If beta is 10%, 1 minus beta is 90%. So the first column, you can see alpha equal 0.05 and the power is 80%. The second one, alpha equal 0.05, the power is 90%. The third column, alpha equal 1%, which is 0.01, and the power is 80 and 90. So we have two scenarios, actual alpha equal 0.05 or alpha equal 0.01, and the power is 80 or 90. So that's why we have 4 columns, okay? So let's take the minimal, because usually in our clinical trials, we take alpha equal 0.05, that's the first column actually, and the power is 80%, unless you have money. Because you're gonna see the more you increase the power, then the more the sample size is gonna increase, and the more you decrease the alpha also, the more the sample size is gonna be. Let's take the first one. So the column, so remember our parameters, P0 equal 0.05, P1 is 20%, and when I look at alpha equal 0.05 and power of 80, I find 4/27. It says 4/27. So this means you need to start with 27 people. That's your sample size. And your boundary is 4. Okay? So if you observe 4 or more out of 27 with your response, you take that drug to phase 3. If you observe less than 4 responders among the 27, then basically you stop the trial. That drug is not good. So, and how much is 4 out of 27? If you divide 4 by 27, how much? Divide 4 by 27. Maybe 15, 16%, I think, something like that. 15%. So basically we're saying if you observe about 15% or more responders, then H1 might be correct. We take the chance with H1. If you observe less than 4, if you observe, can you divide 3 out of 27? 3 over 27, how much? It's 1 out of 9. 1 ninth is 0.11. So if you observe 11% or less, then the drug is not good, so you don't go, okay? And again, you can use any of those, and you can see if our P1 is much further away from P0, and this is something that you should know for statistics, not necessarily here. If two drugs are very far from each other, and one has a rate of 5% cure and one has a rate of 50% cure, usually you don't need too many people to prove it. The more you are farther away from this, it's very easy for us to prove. The more the two drugs are closer to each other, the bigger the sample size you need to prove that they are different. And this is true what you see here. When you look at the first column, and if the difference between P0 equal 0.05, if P1 is only 10% instead of 5%, so if the difference is only 5% between them, you need 169 patients. If the difference is 10% between them, you need 52 patients. If the difference is 15%, you need 27. And again, once you reach basically a difference of 50%, you need 5 patients to prove it, 4 patients to prove it, and so on. And that's actually very logical of what we know of statistics and sample size computation. So we'll take a break here. This is basically what you see here is called the one-stage design, okay? And this is basically a very simple design. If you're doing a one-stage design, all that you need to know is how to define P0 and P1. So at what level you say this drug is not good, and I'm going to disregard it. And at what level you say, no, this is really promising. P1 is usually easier from P0 because P1 is what you see, at least what the standard drug is doing right now. So if the standard drug right now is doing 30%, you might say it's at least 30%. Maybe I have less side effects and so on. So at least I want the new drug to have 30%. So P1, to decide whether the drug goes is easy. But P0, you say, all right, P0 equal 0.05, no, 0.10, whatever. That becomes the difficult part, is how do you define P0? Because sometimes, and the difference, the P0 to P1, remember, if you make them so far away from each other, you kind of, if the P0 equal 5% and P1 is 30, you need much lower sample size than if P0 is 10% and P1 is 30%. So again, you don't want to favor yourself too much because you and so on. Any other question? And some of these decisions are not for the statistician to decide. And when we do this, basically as a statistician, I tell them what's the limitation with what they choose. So if they choose 30%, which is all of us will agree on, 30% is our P1 because that's the standard drug. If they choose P0 equal 5% or P0 equal 10%, I tell them with this you have that, with this you have that. That's what you're gonna run into, okay? And what's the probability of type 1, type 2 error, how much sample size, and so on. So you put the scenario and they decide on that. All right, so let's take a 15-minute break, okay? So now it is 10:15. Let's come back at 10:30, all right? And then we'll continue. All right. So let's start. So just to recap, so this is the one-stage design. You have to get a cohort of people, and if you reach a certain number of good outcomes, some number of patients with actually responders, basically you say H1 is true, otherwise HO is true. Now the problem with this is that the following is that you need actually to find the results of all the 27 patients first in order to make a decision. And you can imagine, for example, if I take 27 patients, the first 22 patients had no response. It could be the last 4 or 5 had response. So you have to wait for all of those to finish so that you can continue. So these are, we are on slide number 20. These are the comments on one-stage designs. They do not allow for early termination. So maybe actually the drug is so good, we should stop early. Or maybe the drug is so bad, we should stop early. So we have to think about this. Uses on average more subjects than other designs that you're going to see in a minute. Okay? And sometimes we are using, there is no control group, we are using historic controls. So again, we talked about why is actually historic controls might not be the ideal thing to use. To resolve these issues, we can use what we call sequential designs. There's 2 of them, fully sequential designs and then group sequential designs. And I'm going to talk about mainly group sequential designs because you're going to see in a second, fully sequential design is not really that interesting. It says monitor intervention effect after each patient. So cannot use endpoints that need long duration because I have to wait for the results of the first patient to come in order to recruit another patient or to start a new patient. So if I'm looking, for example, at survival, progression-free survival and things like this, I really have to wait for like, I don't know, 6 months, 8 months, 1 year to get the results of the first patient to be able to enroll the second patient in. So that's not it. So it takes longer time to finish and becomes complicated in multi-center trials. If you're doing multi-center trials, we'll talk about this maybe today or next time. If you're doing multi-center trials, the coordination has to be very good so that once you get the results from one trial, especially if you're going to start another person from another center. So these become more complicated if it's fully sequential. So people are actually using more, and this is actually what we did here for AUB, in the study in AUB. We did actually a 2-stage design. It's called a group sequential design. It's a 2-stage design. So 2-stage design is the following, and you'll see a graph after this in a second. You start by putting N1 patient on the treatment. N1 patient on the treatment. Let X1 be the number of responders. If X1 is less than or equal to a specific cutoff, R1, then we stop the trial and reject the treatment. So if the number of responders is below a minimal number that we find, we have fixed, then this is not a good treatment. So you stop the trial and reject the treatment. If X1 is bigger than that, so we got really good number of responders, then we continue by putting an additional N2 patient. So the total sample size will be N1 plus N2. That's what we call N. Okay? So we put the second cohort N2. Now we look, and suppose X2 is the number of responders from the second cohort, the N2. Look at the total number of responders now, X1 and X2, and compare them again to another cutoff R. If that total number of responders from the 2 cohorts is less than a specific number R, we reject the treatment. Otherwise, we accept the treatment. Okay? So what's the advantage of this over the 1 stage in this case? Here we're doing 2 stage. We take the first cohort. After the first cohort results come back, we could either stop the trial because the drug is not good, or we continue with an additional cohort. Okay? And then we look at the total now. If we continue, we look at the total. And in the total, if we have good number of responders, we say the drug is good. If we have actually still a non-sufficient number of responders, then we say the drug is bad. So what's the advantage of this over that? You can see there is a graph on 20, there's a flow chart on 23. Again, stage 1, put N1 patient. X1 is the number of responders. If X1 is bigger than R1, bigger than a specific cutoff, then actually go with N2 patient extra. The total now is N. If the total number of responders is bigger than a specific, again, cutoff, then accept the treatment. If the total number of responders is lower than that cutoff, stop and reject the treatment. In stage 1, you could have rejected the treatment. Okay? If in stage 1 you didn't have enough responders from the first cohort, then you could have stopped the trial. So what's the only one main result, big difference? you can early stoppage. So you can stop after the first cohort. So if the drug from the first cohort was not promising at all, you could have stopped there and did not actually involve additional number of patients. So that saves you patients, saves you, especially if the drug is not good. Okay? Now, without going further from here, what addition, what modification we can do on this to make it even better? Without looking at your slides, what addition actually we can make this to make it even more efficient? What do you think we can do? Sorry?
Another entry.
What's another entry? Now here we said our main advantage of this two-stage is that at stage number 1, if the drug is not good at all, we can stop. How about if the drug on the first stage was really great? And you took 20 patients on the first stage, 20 patients cured. Wouldn't that command stop to accept H1 instead of stopping only to reject the drug? And here in this two-stage, we are only stopping to reject the drug. If the drug is not good, if the number of responders is lower than a specific cutoff, we say this drug, even if we continue, is not going to be good. So let's not continue. We'll stop at stage number 1. What if the drug actually at the first stage, we have another cutoff. Instead of R1, the cutoff for bad things, we have an R2, or for when actually, if out of 20 I observe 18 responders at the first stage, again stop and say this is a good. So that's another modification that we do have, okay? But not in this one. You'll see it later on. But this is basically something we should think about. Stop also when something is good. And you'll see at the end of this course, when I start talking about interim analysis, is that we do have that option. We actually stop when it's not good, and we stop actually when the drug is excellent. Because ethically, if the drug is excellent, you should stop and give it to everybody. You should not actually wait for another 20 patients. Okay? So, but usually, either way, by the way, either way, stopping whether the drug is bad or stopping whether the drug is excellent is always, especially in the phase 3, you see it in the interim analysis, we don't make the decision easily. Yani we need to have very strong evidence that the drug is bad or not good at all, and we need to have really very strong evidence that the drug is actually excellent before we stop. For several reasons. I'll give you a couple of them. The first one is that at stage number 1, we don't have a large sample size. So we're deciding on really 20, 30 patients, although the study might have 100 patients. So unless it is convincingly really superb, we don't stop. Or unless it's really very bad, we don't stop. So that's one reason. Also, the second thing, if you're doing randomized trials, and you want to stop early, if you stop early, maybe the two groups that you randomize are not really balanced. So maybe the efficacy that you're seeing is not due to the drug, it's due to because one group is a high risk group and the other group is a low risk group because of randomization is not yet complete. So we'll talk about that actually next time. Why randomization is important in clinical trials in phase 3? Because randomization will create two groups that are actually equivalent on everything. For example, average age is the same. Percentage of males and females are the same in the two groups. The percent of severity of the disease is the same. So when you compare the two groups, they are almost equal, but one group took drug A, the other group took drug B. So when you see A is better than B, say there's no confounding effect. There's nothing going to change. This is a pure effect. That's why we say a randomized controlled trial is the best evidence for causation. Because the groups, especially for example, if you are able to take identical twins or even the same patient, give them two drugs, and then you saw that the drug A is better than B, then because this is the same patient, let's say, then that's an evidence that it's a drug effect. It's not nothing else. So if you do that, but you start actually at the beginning, when you start randomization at the beginning, you might not have equal groups. Basically, randomization happens over the whole sample size. So at the end of the recruitment, the two groups should be equal. So if you stop early, maybe after 20, 30 patients, you're not going to get equivalent group of patients. And that's what Data Safety and Monitoring Board. Yesterday, Dr. Fleihan mentioned it very safely. Any clinical trial usually have what we call a Data Safety and Monitoring Board. This group is different from IRB. The IRB looks at the scientific and the ethical issues. The Data Safety and Monitoring Board, as it says, Data Safety and Monitoring, what we do, actually, I am the head of the Data Safety and Monitoring Board at Cornell. We are actually, usually every study has its own DSMB, but in Cornell we decided that we're going to have one DSMB for all the clinical trials. Actually, we are the only one in Qatar. Hamad Hospital have few of them for specific clinical trials, but usually all of us, our boards on there. So what happens is that before the study starts, when you get the ethical approval, the PI has to send us a plan of how he's gonna report severe adverse events to us, how he's gonna report early signs of efficacy to us, and the quality of the data. If the quality of the data is bad, you should stop the trial. And if I look, for example, we tell him after every 4 patients, we want to look at the data. We want to look at comparing, even if it's a trial, comparing the drug to this. And then basically what happens is that we get the data. The PI does not know because he's actually blinded, most of the times blinded to the results. We get the data unblinded from an independent statistician that does that. And if we see that a lot of people on the drug are having the severe adverse events, we stop the trial. We have the right to recommend for IRB to stop the trial directly. IRB also will look at the events by itself, but they would not look at the whole data set to look at the events. We might ask for more analysis in order to detect whether this is from the drug, this is from other effects, but basically that's what we do. And we, depending on the severity of the cases, we ask the PI to report every 5 patients, every 10 patients, or every 6 months could be. Some trials are not, the risk factor is very low. So you tell them every 6 months, give us a progress report. And the progress report, basically, beside the severe adverse events or the adverse events, which actually they come within 24 hours. If there is a severe adverse event or they come within 24 hours, and we decide on them. So for example, the other day we got actually a severe adverse event. A patient that actually was in one of the studies was hospitalized, okay? But the PI sent to us that they recruited this patient, they got hospitalized, but the patient had not been randomized to any of the drugs. So it was still in the recruitment. So we said, it's all right, you continue. So the hospitalization has nothing to do with the drug because this patient was not anyway, at the time of hospitalization, we're not randomized yet to any of the drug trials. So again, so these are the issues we get. We have a trial actually that deals with mental health, medication for mental health. And we brought the attention to the IRB. The IRB didn't feel that this is important. We thought maybe there is a question in the questionnaire whether the patient actually thinks about suicide. And we said, how about if this medication increase suicidality or ideation of suicide? We should monitor that because that's something important. Physicians at the IRB thought that actually there's a very little risk. The medication is very well known and there's very little risk. As a DSMB, we said, no, we want to monitor it. What's the problem with it? We don't know, and we want to monitor it. So we decided, we told the PI, and the IRB had to approve that actually, is that you need actually to give us reports every 4 patients, 5 patients. We want only the answer of that question that you think about. Of course, if somebody tried to commit suicide or committed suicide and died, that will automatically comes to IRB and us as an SAE, severe adverse events. But even we're trying to monitor increase in the suicide, we call it suicide ideation, so thinking about suicide. And we told them we need every 5 patients to look at that. So this is what the Data Safety and Monitoring Board will do. So again, so here you can stop early to reject, and the other modifications stop early to actually accept if it's the drug is too good. Again, there are some limitations with these. Now, on slide 24, you can see that there are 2 different, there's so many of those designs that we just talked, the 2-stage design. There's the ones that are famous, we call them the optimal and the minimax two-stage design. So basically here you specify alpha, the probability of type 1 error. You specify beta, the probability of type 2 error, or to the power 1 minus beta, the same idea. You specify P0 and P1 as we did before, P0 and P1. Remember, HOP is less than or equal to P0, H1P is bigger than or equal to P1. And this will give you a unique solution if you do one of those, minimax or this. Otherwise, you have a lot of solutions for N1, what's the number of first cohort, R1, the cutoff, the first cutoff, and N2 and R2, or the total sample size, and R. Now, so there is a lot of solutions if you only specify alpha, beta, P0, and P1. So in order to get a unique solution for those, in other words, get these numbers and do the study, Simon suggested two things, is that let's look at studies, and he called them optimal and minimax. Let's look at two additional factors. What is the expected size of the trial if HO is true? So if the null hypothesis is true, and I repeat this study 20 times, on average, what's the sample size I use? Again, like a simulation, okay? And he looked at another one, it's called the probability of early termination, again, if HO is true. So if HO is true, you want actually the probability of early termination to be high, if HO is true. So he wants that, and he decided on two, depending on these parameters. So the optimal design chooses your parameter N1, R1, N, and R, which will minimize the expected, on average number of, if you want, expected number of patients basically is called the average. So the word expected number is average. So the average number of patients if HO is true. So it will minimize this. The minimax design will give you the cutoffs N1 and all these cutoffs will minimize the maximum sample size of the whole study. So remember, what's the sample size of the study? If you have a two-stage study, N1 plus N2 is the sample size, the total. If the study continues, it could be N1, the total sample size if you stop early. It could be N1 plus N2 if you actually go to stage 2. So how do I compute the total sample size of a study? If you have a study, you have N1 and you have N1 plus N2. So if you stop at stage 1, you have the total sample size is N1. So some studies, when I do simulations, some of them stopped at N1. And then that's the total sample size. Some of the simulation, when I did it, it actually went all through, and N1 plus N2 was the total sample size. How do you do the average? How do you do the average if some of them stopped at N1, some of them stopped at N1 plus N2?
Like N times how many?
Exactly. So if N1 stopped, if 30% stopped at N1 and 70% stopped at the full sample size, so you say 30% times N1 plus 70% times N1 plus N2. Okay? So it depends also on the probability of early termination. So basically, the average sample size of a study would be N1 times the probability of early termination plus N1 plus N2 times 1 minus probability of early termination. So as I said, if the probability of early termination is 30%, so 30% times the sample size of the first cohort, 30% times N1, and 70% times the full sample size. And that will give you the average. Okay? Now, so minimax, the minimax design will minimize the maximum sample size, and the optimal design will minimize the probability of early termination. So it picks the best one that actually has the expected number of people under PO. Now, these are basically, there are tables, but here you can see I put a link. This link is actually from NIH. And if you click on the link, it will give you a website. All that you need to put in this website on these, you need to fill 4 things. You need to fill P0, P1, alpha, and beta, or 1 minus beta. So you can see that the first here says enter probability of acceptance of poor, alpha. So the first one is alpha on the top. Let's say put alpha equal 0.05. Let's take an example. I'm going to put here, alpha equal 0.05. And the second one, put actually beta. So they don't ask you about the power. They ask you put beta, which is the, let's say 0.10. So that's 10%. These are the most typical ones, or 0.20 is usually used for beta. So if beta is 0.10, the power is 90%. If beta is 0.20, the power is 80%. And then it tells you put P0, the third entry, put P0. Let's put P0 0.05, okay, 5%. And P1 is 0. Let's say 20, okay? So P0 and P1 is 5% and 20%. These are, P0 is the probability below which we think the drug is so not good. And 20% is the one that we think that the drug, actually, if we reach at least 20% or more, this is a promising drug, let's go. And click on calculate, then there's click on calculate, and you get this table. At the top left, it tells you what you entered. You entered alpha equal 0.05, beta 0.10, P0 0.05, and P1 is 0.20. And it gives you this table. On the first column, it gives you the titles of the rows. Okay, on the second column is the optimal design, and the third column is the minimax design. So what's in the optimal design? It gives you, the first entry is 21, that's N1. So that's the first stage, sample size N1. And directly below it, it gives you R1, which is the cutoff for the first stage. So in this picture, let's say I'm using the optimal, 21 and 1. So 21 is the first cohort, and the cutoff is 1, okay? So this means that if I get what, 1 or less, then I'm going to stop the trial, okay? And the drug is not good. If I get more than 1, I can continue. Okay, let's go back and just go back and to see that here, okay? So if X is 1 or less, you stop. So that's the cutoff. If the total number of responders is 1 or less, you stop and then basically reject the treatment. And if it's more than 1, and if it is more than 1, you're going to continue. Now the third entry in the table says the maximum sample size N equal 41. So basically on the second cohort, you need to add 20 people. So you have 21, the total should be 41. So on the second cohort, you add 20 people, and the cutoff is 4. So this is the cutoff for both cohorts together. So after 41 patients, if I get 4 or more, the drug is good. If I get less than 4, the drug is actually not good. Again, you can go back here, and so if you get more than 4, not 4 or more than 4, then the drug is good. If you get 4 or less, you stop and reject the drug, okay? So basically, we're just filling in these cutoffs that this. And if you want to use the minimax, you start with a cohort 29, still the cutoff is 1. And then if it works, if you continue, if you have more responders than 1, and you continue, then you need only to add 9 more patients, and the cutoff is 4. So of course, when you look at this, the total under the optimal design that you can go up to is 41. The total under the minimax is 38. And that's why this is called the minimax. So it's minimized the total sample size. Not only that, the probability of early termination under the optimum design is actually 0.72. So there's 72% chance terminating early if HO is true. However, this is better, the minimax is better. If HO is true, it's 57% chance of early termination if it's actually true. So basically, these are the designs, and you can pick any one of them depending on what you want. Okay, so we did a similar designs here for AUB. I'm just trying to remember what was P0. Alpha was 0.05. I think beta was 10 or 20% beta. I remember P1 was 30, but P0 maybe 15, if I'm not mistaken. Let me just check it. I know from the numbers. We had around 41 patients, actually. So P0 equal 0.05, P1 is 0.20. That's power of 80%. Still acceptable power of 80%. And I think this was 0. The P0 was 0.15, and then P1 is 0.30. So 30 was the decision. Yeah, I think we looked at this minimax, if I'm not mistaken. Something very similar to this. So the total was about 45 patients that we got. And at the first stage, we have to have actually a good response of about 13 or 14 to continue to the second stage. And I had actually to describe this to the oncologist, because I told them that you cannot recruit on the second stage until you finish the first stage. And because there might not be any second stage. So the first stage, after the first 23 patients, you might stop the trial and say the drug is actually bad. Okay? And that's why but they said the outcome is immediate. So the outcome that they're gonna get is not progression-free survival, it's actually directly response after like 2 or 3 weeks of some kind of medication. Okay, and then they do that. So they said it's fine with us. We can actually directly, and we can recruit fast, because these are actually the response. We get the response very quickly. It was a complete response. They want a pathological PCR, pathological complete response. Okay, so these are the things that we do. So this really, I cannot share the details, but that's basically was like 2 weeks ago when I did that. This is slide 26. Here we took an example of slide 26. We took alpha equal 0.05, beta equal 0.10, P0 0.20, P1 0.40, and the optimal design starts with a cohort of 19, a first cutoff of R1 equal to 4. If this doesn't work, I mean, if actually the drug is good, you continue to the second step, and you need a total of 54. So you add an additional 35 patients. And the final cutoff is 15 out of 54. And if you reach more than that, more than 15, then the drug is promising. 15 or less, the drug is actually not promising. And the average number of the total sample size, if HO is true, is 30.4%. And the probability of early termination, if HO is true, is 67%. Under the minimax, you start with a bigger cohort of 24 except of 19. Your cutoff is 5. If you have a good response, more than that or more, then you continue to 45. You put additional 21 patients, and the final cutoff is 13, which means if you get more than 13 patients and out of 54, the drug is good. If you get 13 or less, the drug is not good. Again, on average, the total sample size will be, if HO is true, is 31.2. And the probability of early termination, if HO is true, is 67.6% or 0.676. So these are things. So on the homework, I will send you a homework actually, and we'll give you scenarios like P0, P1, and you have to describe, what to do. And sometimes I will tell you, suppose in the first cohort we get 10, what should we do? Okay. So for example, if you're using any one of those, the cutoffs for the first cohort are 4 and 5. So if you get 10 responders in the first cohort, you should continue to the next cohort and put additional patients and so on. Now, other designs, we have something called the modified Simon designs, 3 outcome, 1 stage design. So the 3 outcome that we talked about is that you can actually have stop the trial if the drug is bad, or stop the trial if the drug is good. So that's for the 2-stage designs. So the third outcome is being here, stop the trial, and then people added the third one for the 1 stage is inconclusive. So if you get like on the first stage, okay, let me explain this so that you understand well. You might have actually, so I'm gonna do here a 3 outcome picture. So we're going to start with a cohort, whether it's one stage or two stage. We're going to start, this is the first box with a cohort of, let's say, n equal to 50. Okay, whatever number it is. You will have actually two cutoffs. Let's call it R0 and call it R1. R0 is the number, if you get that number or lower, you stop the trial, if actually because the drug is bad. So I'm going to just put numbers. Suppose R0 equal to 5. So if I get responders X equal to 5 or less, then basically stop trial and HO through. Okay? R1, let's say, is equal to 20. The second cutoff is 20. If at the phase stage, again, if I got X equal to 20 or more, then stop trial because drug is good. Okay? And then this basically accept H1. So H1 is true. However, what if I got a number of responders between 5 and bigger than 5 but less than 20? That way, if you are doing one stage, then you say it's an inconclusive study. Okay? So if the number of responders X is between 5 and 20, does not include both of these, between 20 and 20, we say it's inconclusive. In a two-stage design, you might go further one more step, is that if it's two-stage design, you might actually add another stage, and then you might at the end still reach inconclusive. Okay? In one stage, it's only one stage. You stop to accept HO, you stop to accept H1, or if it's in between, it's inconclusive. And if it's two-stage, the same thing at the first stage, but if it's inconclusive, you take another cohort, and then you might still end up with an inconclusive at the end. All right. So these are, so again, the literature is full of these, full of those different designs. The ones I'm giving you for phase 1 and phase 2 are the most common one you see in the literature. And when you look at the phase 2 studies in the literature, you see a lot Simon designs, Minimax or Optimal. These are the most used ones. Okay? And they are very easy to implement. They are actually straightforward. They have the alpha and the beta that you desire. It's the choice of P0 and P1 is the only thing that people actually have to agree on. Okay? So the third outcome is being inconclusive in addition to rejecting HO or rejecting H1. Thus, we have two boundaries, R and S, or I call them here R1 and R2. And usually, of course, the boundary for rejecting HO should be less than the boundary for accepting S1. So if I want to accept H1, I should have a high boundary, high cutoff. And if I should accept HO, the boundary has to be low. So that's very, very close. Now, again, in all of those, so far, one stage and two stage design for phase 2, we have not have a control group. There was no randomization. We take a group of patients and so on. Now, why do we do this? Why don't we have a control group? I'll tell you from practicality and from statistics why. All right. Suppose we have a drug on the market, okay, that has a response rate of 30%. Now, in order to do a study where you're going to prove your drug is better on a, if you want, one by one, randomized trial, then your study has to be large enough to get, you have to expect what difference how better is your drug from the 30%. Let's say your drug is 40%, okay? And basically, you have to find the sample size and do randomization and find this. Now, people don't do that for two reasons. Why they don't go for face-to-face if you want comparison, okay? The reason is, the first one is that now in the real life, we're not finding like one drug that's so superior than the current standard. Very rarely now, you read in the literature, unless it's a breakthrough. But if it is a same drug but used, for example, now some drugs, let's say, are used for lung cancer, are now trying to be used for other types of cancer. Okay? You don't expect really a huge rate, but you might expect as good as the standard drug. But maybe your drug is kind of less expensive, good quality of life, and so on. So what people is trying to do is that they're trying to, especially pharma companies, they're trying to, if you want, take advantage of these good drugs that they have and try them on other types of cancers, and to be able to see if they do as good as the standard drug that's available there. Okay, and then this way they get part of the market share. Okay. Now the other thing, so in statistics wise, that's the reason, if you want, from the pharma companies. They don't want to go into one-to-one because it's very hard. Their drug probably is only as good. Okay, even if it's better, it's going to be better by 2, 3%, 4%, and that, if you want to do a face-to-face or comparison, is going to need like 10,000 patients to be able to do it. So none of the companies will be able, and this is not only in oncology, I've seen it also in hypertension drugs and things like this. They don't go to face-to-face comparison because these actually will cost a lot. And the result of this, if they go this, will destroy one of the drugs. If I prove that drug A is better than B and I publish it, then so a lot of the time is they go over the standard, or what we call a historic control, or they go over what we call a placebo. Okay? In cancer, you cannot go over placebo, but in other types of diseases, they might go over placebos. So head-to-head comparisons are tough from a statistical point of view, especially if the drugs are very comparable in response rates. Okay. All right. These are different. Now here, when we start randomizing patients, then here we're trying to do actually a head-to-head comparison. So you can have randomized phase 2 trials with a control arm, and then you see randomized phase 2 trial without a control arm. Here, these are called, some people call them also selection trials. So this is basically where actually you're trying several new drugs in phase 2, and you're picking the best of them to take to phase 3. Okay? And this is what a lot of people try. They try different, it could be different doses of different types of drugs, or different cocktails of drugs. They try it at phase 2, and they say, all right, most promising one will go to phase 3. Again, if it actually also satisfies certain criteria of percentage of responders. But the best, so we want to pick the best of them to take. So let's think about the first one with the control arm. So randomized phase 2 trials with control arm use new treatment and standard treatment, crossover design after the progression of the disease. Okay, some people use that after the progression of disease. It's not necessary for doing a crossover study. Okay, you have to, the word crossover has been very misused by a lot of people. Crossover design, you're going to see later on. I'm going to actually show you the design. We're going to analyze data from the design. The crossover design is patients takes at the first stage either drug A or B. Then you stop the trial. And so you let the patient with no drugs until, and the patient has to get worse. If you cure them, you cannot do crossover studies. So you stop them, and the patient gets worse until they are almost at the baseline before they started the first drug. And now you give them drug B. You switch them. If they were on A, they get B. If they were on B, they get A. So basically, each patient becomes his or her own control. Each patient took A and B. Again, the main condition is that when we stop the drug, the patient deteriorates until they become as bad as they were before we demonstrated A. If there is, we call this usually the washout period. If actually the patient still by the end of the washout period still is really very good, then you cannot do crossover studies as a study design.
That patient will not be included.
No. If you know that from the beginning, you would not do a crossover study. Okay? Sorry? Yes, I'll tell you when. The crossover studies are not studies that you do on anything. You do it, for example, for pain management studies. Pain management. You give them a painkiller, they get better. When you stop it, they still feign pain, but you actually, until they reach the same level of pain, then you try the second one. Of course, if there is risk on the patient, you're not going to stop, okay? So these are done for chronic diseases where actually stopping a drug is still ethical. So that's why. Now, this is crossover studies. Now, some people use crossover, the word crossover, they say we crossed over the patient. For example, in oncology, for example, you do initial treatment, new treatment, standard treatment. Once the study is over, you might cross over them to other thing, but the study is stopped. You cross over them, especially, you might not cross over both of them. If the new treatment was better, you provide the patient who took the control or the standard treatment, you provide them with a new treatment for the same amount of time. Okay, so I started, some people took A and B. A is the new, B is the standard. At the end of the study, A was better than B. So people who were on B, I provide them A for another like 6 months. Okay? And the reason we do this is for improving recruitment, because this, you promise the people on the standard drug, you tell them, listen, if the new drug is better, we'll provide you the new drug for another 6 months with insurance usually. We ask the pharma to do insurance. Okay? But it's not a crossover study because you're not actually comparing the results between this and this. Okay? So that's why, and these patients, I mean, after the new treatment are done, they are new patients, they are different patients. They are not, I mean, if you did surgery on them and then you did some kind of therapy, they're not the same patient. So they cannot actually do it like pain management and things like that. So, but the people use the word crossover. Okay. So this crossover after the progression of the disease is really, sometimes is done as a crossover study, for example, chronic diseases where pain and things like this. But and sometimes they are just do it as a recruitment strategy for people actually to come, and you promise them if the new drug is good, we provide you with this new drug free of charge for the next 6 months. Okay, so be careful, please, about using the word crossover. So the objective in this is not to compare the new drug to the standard drug, but to help in interpretation of a poor response rate to the investigational agent, so the new drug. So in other words, they might not be fully powered studies. Okay, if it's a fully powered study, if there's a big sample size and things like this, we get p-value, we compare the drugs. But sometimes you do them parallel line just to see, for example, we know the standard is 30%. But maybe now, when we're doing this study, as I said, the standard of care are different now, and we're treating the patient different. So we want a current standard results. And we will look at it, maybe the response rate is 25%. If our drug is doing close to that, 25%, we say our drug is comparable. If it's doing much, much less than that, then you're saying, no, this drug is not good. So there is no, if you want at the end, there's no p-value for that study. But there is actually a comparison and expert's opinion. And this is what's crazy about this when you read some papers. Okay? Sometimes the expert opinion, and this, we'll talk about this in non-inferiority trials later on. In non-inferiority trials, if you want to prove that your drug is non-inferior to another drug, what you do is you say, if my drug does less than the standard drug by 5%, we will call it non-inferior. And there's a sample size computation, by the way. That's a phase 3 trial. And there's sample size based on that decision. So that 5%, who decided? Some people say, if we are lower by 20%, we are good enough. And this is, you'll see, I show you some publication, really crazy publication, where people said, if our relative risk is 0.6 compared to them, then actually, so 40%, not the cure rate if you want, is 40% less lower, then we're still non-inferior. We have non-inferiority. And I look at it and I was like, are you serious? 40% lower and you still, but relative, not absolute difference. Yeah, and this is oncology study. It's not like it is something, a headache study. And basically that was published, I'm talking to you, in one of the biggest journals. And the main controversy, I read it, the whole thing, the main controversy is how they decided that 40% is actually to them a non-inferiority, it's all called a non-inferiority boundary. And they said it was an expert opinion. That's all that they said. It got published in the biggest journals. But this is basically, we'll talk about that later on. All right, so here we don't have that. So if the response rate of the new drug is large, more than 25%, then it's declared as having anti-tumor activity. If the response rate of the new drug is small and that of the control is large, then the new drug is not effective. If both of them are small, so you have a comparison. Both of them are small, you say both of them are not good. If the standard is giving 20 and the other, we got 25 or something like this. So basically it's just a comparison between the two to make a good decision. If both rates are small, the trial is inconclusive and so on. Okay? Any question about this? And finally, randomized phase 2 arm without a control trial, you have 2 or more treatment arms. Each arm represents a new drug. So you randomize patients into several new drugs, and basically you want to pick the best of them to take to phase 3. So an advantage of doing this, all of it centralized, is you have central registration. Randomization is really good because when you do randomization, you register all the patients. So how it happens, we'll talk about it next time. Is that I create a randomization sequence, which basically I say patient number 1 takes A, 2 takes B, 3 takes A, 4 and so on. So when I do this, I have to register all these patients. So the physician will call me and says, yeah, we have a patient. I'll ask him if there's eligible, non-eligible, sign the consent. They say yes, 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 yes. And then I tell them, all right, this patient will get, this is number 23, he'll get A. So we have a central registration of patients, and differences are likely not to be biased by heterogeneity of patient and response evaluation, especially if you're doing this in one center, because we are randomizing patients. So even if the patients are heterogeneous, when you randomize them, the randomization will make all these groups equal. Okay? Limited by sample size, but important estimation of the degree of activity or level of toxicity, etc., for each drug will be reliable, help rank the treatments using some kind of statistical theory. So basically, we have all of this, we're going to rank them. We're going to say this is the best among those, the second best, and so on. Sometimes you might be able to compare them using non-parametric statistics, something actually statistics that depends on ranking only, not on the actual response rate. So it could be that the response rate is 30 for drug number 1, 50 for true. So we don't say this is actually 20% difference. We say number 2 is number 1, ranked number 1, the best drug, and this is ranked number 2. Because we don't know if that, because of the small sample size. Imagine like this, if you have 5 patients on each one of them, if one drug had 4 response out of the 5, how many, what's the percentage of response? 4 out of 5 is 80%. If the other drug had 3 out of 5, that's actually 60%. But it's really one patient, that's the difference. So when you're dealing with small sample sizes, you don't worry too much about the percentages, because a one patient, even if it's 10 people total in each group, a 1 is 10%, 1 out of 10 is 10%. So a one patient difference could be a 10%, and one patient difference could be a 20%. And that's why we rely more on ranking rather than comparing them, for example, using a t-test, things like that. Okay. And then the best treatment, sometimes not only one, more than one, regardless of the magnitude of its advantage, are selected for further investigation. So again, regardless of whether it's more by 20% or 30%, we pick number 1 or number 2. If we can afford 2 of them, we can pick 2 to the phase 3 and do head-to-head comparison along with the standard drug in a bigger study. Now, also this have some kind of sample size computation for this kind of studies. So sample size is computed in a manner to ensure that with a certain probability P, a superior drug, say by amount of D from all other drugs, will be selected. So this is basically the idea is that if there is a drug that is better than the rest by amount of a D, okay, then that which should be selected with certain probability, let's say 90% probability, will be able to select that drug. If 2 such superior drugs are found, then the selection approach will tend to pick one of them with probability also P. This is actually a sample size computation. This table, and you can look, actually there is on this link, there's more information. I'll click in a second. But basically here, if you're comparing 2 treatments, you can see number of treatments. So the left column, it says the smallest response rate. So what's the smallest response rate? It could be 10%, 20%, 30%. So it goes up to 80%. The second column is actually talks about if you have only 2 treatments to select one of 2. The third column is you have 3 treatments, you want to select 1 out of 3. And the last column is if you have 4 treatments, you want to select 1 out of 4. And here basically, suppose we know the smallest, and if we have 3 treatments and the smallest of the response rate is 30%, 30%, and we have 3 treatments, then the sample size is given for 30% and 3 is 52. And this is per arm, so 52 per each arm, okay? So basically, with this number, so this I think I give an example here. Suppose we have 3 treatments and expect baseline response rate, which is the smallest 20%. So we need 44 patients per drug so that we can, with 90% probability, choose the drug who has a true response rate of 35%. So I go back here. If you go to 20%, oops. Okay, if you go to 20%, 20% smallest rate, remember this table at the top, it says P equal to 90, D equal to 15. Okay, if the smallest response rate is 20%, you want, if there is a drug more than this 20%, by that D, 15%, you would have 90% probability of actually picking it. Okay, and that's why you need 44. That's what the 44. So it says, if I get 44 patients per group, according to this table, if I get 44 patients per group and the baseline is 20%, if there is a drug that's better than this by 30, reaches 35%, then this actually randomization, we be able to pick one of them. Actually, there's 90% chance of picking it. And there's 10% chance of not picking it, but there's 90% power chance of picking it. Let me just click quickly. I haven't looked at this website yet in a long time, but we can look here. I have to look back into the link. So let me fix this and then we'll look at it later on. So basically, this is the phase 2. So again, we repeat what in phase 1 and phase 2, this is really an introduction. This is not, the course is mainly about phase 3. So phase 1, what I want you to know is these 2 simple designs that we talked about, along with what is the objectives of the phase 1 and what are the ethical issues. In phase 2, again, I want you to know the designs. I talked to you about the optimal designs, the minimax design. Phase 2, we start seeing more than phase 1, the 1-stage, the 2-stage designs that you've seen. And the last one is selection designs, is that this is basically you randomize several drugs and you pick the best of the best if you want. If it reaches a bigger cutoff that you design, like 15% more than the rest or 20% more than the rest. So there are tables different than this that you see on slide 34, that are tables that for differences, 15%, 20%, 30%, 40%, you can be able to pick the drug. Any question about this? So what you're gonna expect from me on at least phase 1 and phase 2 is I'm gonna send you a homework. Please, the homeworks are not meant for you to, if you want just to, if you have any problem with the homework, you can email me. It's like practice exercise, but I give you actually credits for doing them, okay? You have to submit them. There is a deadline, you have to submit them, but you are welcome to work within each other on the homeworks. So if you want to collaborate with each other, but also you are welcome to send me emails and say, Ziad, question number 1, I don't know what to start, how to do. And can you give me a hint? So these are more practice because we don't have time to do a lot of practice here. And they will be very simple. And if from only the slides, you will be able actually to solve them. So I'll give you a scenario. I'll say, all right, we have P0 equal to that, P1 equal to this, alpha and beta equal to this. Give me the minimax design. So you'll go to the website, you get the minimax. And I'll say, all right, if at the first stage you did this, what happens? If we get on the first stage 50 responders, in a phase 2, what happens? I'll ask you some multiple choice question about ethical issues and designs and things like this. Again, as I said, these are more practice in nature, and this what will come on the midterm and the final exam. So it's not just collaborating or just, you need to understand the questions and understand why are they. By the way, our midterm and final are open book exams, okay? So, so if you want to take notes and things like this, these are open book exams. And starting next time, I'm gonna start introducing you to Stata. I don't know of how many of you know how to work on Stata? Can you raise your hands? So a lot of people, but the others, if not, we'll introduce you from zero. And there is no need to worry about. I know the sharp student did SPSS, but the Stata, you'll see, you'll like it a lot. Okay, and the Stata we will do a lot of. If you want, the words are going. It's not point and click, so we do more syntax than this. So, but this is for next time. So what I'm gonna do now, I'm gonna give you another break. I'm gonna start on phase 3, although this was not actually on your on our things, but because I want to gain, we still have an hour to go. The first few slides on phase 3 are only more definitions. So I'm gonna go through these definitions. I'm gonna go through like 1 hour of them, and then I'll post the lectures on Moodle. But you don't need even to take really notes. If you want to take notes, just take notes for yourself. But these are definitions. So let's take another 15-minute break if you want to get water or something. And then we'll start on phase 3. I didn't know that we're going to finish, but that's fine. It's good for us. This means maybe we can, at the end, do survival analysis. So if we're doing a little bit more. So, and then you can ask me any question if you want. If there's anything on the slides later on, you find that it's not understandable. So we'll go quickly next time, review quickly all this. So basically here we're going to talk about phase 3 clinical trials. And phase 3 clinical trials are called in the literature the gold standard of causality. These are the gold standard for proving causality. Now, it's comparative. So this is basically phase 3 clinical trials. In principle, they have to be randomized and they have to be controlled. Randomized means there's a randomization of patient to the groups. Control means there is a comparative arm. Whether the control is placebo or the control is an active drug, that's another issue. But there is a comparative arm. There is a control. That's why most of people call them randomized controlled trials. So randomized controlled trials. And these are phase 3 trials. So comparison, so basically the comparison between the new drug and the current treatment or a placebo in terms of, what are we comparing them? Basically we're comparing them in terms of efficacy. That's our main goal, is to prove that this drug is superior or non-inferior to another drug. But also we always monitor side effect and safety. So again, as I said, side effect and safety is from phase 1 to phase 4. There's, by the way, something called phase 5 clinical trials. We call them translational studies, okay? But basically, that's, so the main objective, if you want, the main objective is to compare the new drug to the standard drug or placebo in terms of efficacy and, of course, incidence and severity of side effects. Now, these are the gold standard because they are full scale. They are basically, there's large sample size, they are powered, they have a control arm, and they are randomized. Now, when you read an article, especially in the title or in the abstract, they write something like this. They say, this study is a multi-center, double-blinded, randomized, placebo-controlled superiority trial. So I'm going to go through these. What do we mean by double-blinded? What's randomized? And I'll tell you, how to do these things in real life and some experience that I have. Once we get to randomization, I'm going to show you how to do your own randomization. But I'll keep that for next because we need to use the computers and we need to use like web pages to do that. Okay, but we'll talk about the different types and then we'll do them. And of course, after this, I'm going to show you how to compute the sample size of the different study designs in phase 3. And then the next lecture will be on analyzing it and what can go wrong with the analysis and how to adjust for different things. Okay? This way we will cover all phase 3 from design to the analysis. And then we'll take special cases, crossover studies, factorial studies, cluster randomized studies, and so on, survival analysis, but all of them. So here I'm going to go really for a simple parallel group design, which is basically 2-arm, A and B only. Okay? So the first word, multi-stage versus single stage, single arm, single site versus multi-site or multi-nation. So basically in a single site, you should do a study in a single site if you can, if the center can provide a representative sample of the population. Now, clinical trials are not like survey. I would put a question mark under representative because clinical trials are not meant for everybody. Clinical trials are very specific. You have really extensive inclusion and exclusion criteria for clinical trials. So they are really for a small group of patients. What I mean here representative is after you actually qualify for a clinical trial, you want all the range of possible patients that are there. So you don't want to do a clinical trial where only you have the mild cases, okay? Because you want to generalize it later on to all patients that actually satisfy the inclusion criteria. So that's why the center has to provide. So I give you a simple example. Suppose I have actually a friend of mine. I have a friend of mine who's a cardiothoracic surgeon. He was in the States, now he's in Lebanon. Now, he's really an excellent guy. In the States, he was really an excellent person. When I came here, I started hearing rumors that people are dying under his supervision. And I called him, I was like, he's a good friend. I said, what happened? He said, I get all the high-risk patients. I get an 80-year-old patient. Nobody wants to actually take the risk with them. I take the risk. I've done. He said, of course, some of them are going to die. But if you look at the profile of my patient versus a regular one, probably I have 20% high-risk patients. These are 80 years old or 85 years old, where actually I go and do surgery on them. And some of them die. So again, if that person might be good to do a study on because he has a full range of studies. If this was one person, one arm versus another arm, that another cardiothoracic surgeon that actually got all the mild cases, then it's not a fair comparison. That's another issue we'll talk about later on. But here basically you want this. For example, why is AUB good to do studies in? Because AUB get different types of patients. Even socioeconomically, it gets different types of patients from all regions in Lebanon, from outside Lebanon they come. So it has a diverse group of patients, okay? So it might have a representative group of patients from all types of... Now the second is very, very important. The center has adequate resources. It's very hard to do a single study. We tried to do a study, very simple study, a new routine, a new way to read MRIs for knee ligament tear. So I didn't know that the MRI, they have protocols of reading MRIs. I have no idea, I'm not a radiologist. But apparently there are protocols of how to read an MRI to make it actually more sensitive and specific, so be able to accurately diagnose a ligament tear. And the study we need 500 patients to do this. and we need to do MRIs on them. So we went to the hospital and we said, listen, we would need to do MRIs for 500 people we recruit 3 times a year for 2 years. They said, it's not possible. The guy told me, if you want yourself an MRI, you need to wait 2 weeks to get your MRI done. So how am I gonna actually add another 500 to my resources? I have no resources to be able to do that. That's one issue you need to worry about. The other issue is staffing, especially if you're doing this in hospitals. Sometimes you expect people to help you, nurses and other physicians to recruit, and sometimes they say yes at the beginning, but then at the end, nobody. I mean, you need to get your own research associate or assistants to be working on, if you have nurses or pharmacists or colleagues, physicians are working with you, they need to be very involved to feel that they are part of the study to be able to give you. Otherwise, the resources are not there. All right. Now, but however, if you are able to do this, and we've done some of studies in only single sites, you have very good you have good quality control. If I'm doing something in one place, I can actually monitor everybody. I can train everybody once and monitor them. Versus actually, if I'm doing this in 5 hospitals or 5 countries or 5, I don't know, continent, then it's going to be very hard to monitor. Okay, so that's why I say there is a consistency in the assessment, so better quality and reliability of the data collected, because you can always keep training and go on. And of course, it's easy to conduct. The disadvantage, it might take longer time because I'm recruiting from one place. So if actually I recruit from AUB and I recruit from the north and from the south of Lebanon, then I get actually patient quickly. So I might finish quickly. And this is definitely not suitable for rare diseases. If I'm doing a rare disease, I'm not going to do a single site study, unless this study is the referral site for all the disease in the country or the region. That's the only case to do it. But if it's not, I'm not going to do a study for a rare disease in one. By the way, rare diseases, do we do clinical trials on rare diseases? Do we do clinical trials on rare diseases? If somebody asks you a question like this, I'm not talking about, for example, a rare form of cancer, maybe a rare genetic disease or something like that. A very rare disease, like 1 in every like a million case. Okay? What is the most suitable study design for rare diseases? Case control studies. So if you're doing a rare disease, it's a case control study. You're not going to be able to do a survey to pick up these rare disease people. You're not going to do a cohort of rare, because if you do a cohort, after 10 years, you get like 5 cases. You're not going to do a clinical trial because you cannot obtain these people. Okay? So the best one is a case control study for rare diseases. This is the most suitable study. But still here, we're talking about, for example, some rare types of cancer. You might actually find a few cases here in Lebanon, in other countries, and you might then combine them in one big study. And that happens a lot in oncology, okay, to get a bigger sample size. All right. Now, multi-center. So single site, we said in the single site study, we need to remember that it's actually good quality control. However, we have to look at the resources, type of patients. We have to look at actually the time duration, because if I'm recruiting from one site, it's difficult. It takes more time. Now, multi-center studies involves more than one study center. The center could be a hospital, a clinic. It could be also another country. Now, here is very important what we talked yesterday. Dr. Flayhan talked about protocols. So you have to develop the protocol of the study and the standard SOPs, the standards of operations for every tiny thing. And these has to be visual, like in the places where you take blood and things like this. All right. So multi-center studies are now common, very common. People are doing a lot of them. I've been involved in some of them. But basically, you have to have an identical protocol. Everybody has to follow it. You have to go train every site on it. So we've done studies here in several hospitals. We have to go to every hospital and train people, okay? And basically, it's good here when you're doing that training is to have a key person in each hospital, okay? We did a study in Lebanon here in 120 hospitals. The budget, I don't remember, but the budget, let's say, was $200,000, maybe more. Half of it was on transportation. It's, I mean, going to the south and then going to the north and going everywhere, you spend a lot of money on transportation. So it's better to get coordinators everywhere. The problem is finding qualified people to be coordinator. I think now, with more people getting degrees in public health and nursing and masters and things like this, because you need somebody to know a little bit of what research means, okay? And this is becoming much easier than before. But we had that issue, is that it takes a lot of money doing that. And then the idea is in multi-center studies, your data is not intended to be analyzed for each center alone. We will analyze it for each center, but the data, if the sample size is 1,000, it's for the whole study 1,000. It's not actually for each group 1,000. So data is intended to be analyzed as a whole. Now, what we love about clinical trials, multi-center clinical trials, is that when you do multi-center, you already prove two things. You prove that you are able to do the study in different settings. In other words, like I did it in a university hospital, and I did it actually in a military hospital, and I did it. So you could replicate the study, which is good, because a lot of the time people actually, when you look at intervention, they say, this is a so complicated intervention. In the real life, you cannot replicate it. So why are you doing this? So when you do these kind of studies, replication is already, you are doing it in 5 centers in 5 countries and so on. It's something good. The second thing is generalizability of results. When I bring patients from all over Lebanon or all over the region, then basically the results I get from this study, because I'm combining all this data together, are more generalizable. So I get different types of patients. I get the wide spectrum of type. Of course, all of them has to include, to satisfy the inclusion and exclusion criteria, but actually do that. And of course, you do shorter time to complete the study because you're recruiting simultaneously from all these studies, from all these centers. So it's something good you can do. Now, the first thing you need to worry about is treatment by center interaction. So what do we mean by treatment by center interaction? First, we gather all the data together and we analyze the data. And let's say after analyzing the data, the new drug A was better than the standard drug. Now, once we start looking at the centers, we find there's discrepancies. In center A is better than B. In center 1, A is better than B. But in center 2, B is better than A. That's called interaction between the center and the treatment. And this is actually the worst kind of interaction, where actually you have flipped results in different centers. Now in principle, this should not happen unless there is something specific about that center, about all these patients, that made these results. So you have to investigate a lot of what went wrong, or what is the reason behind having different results in different centers. You might have actually the same results in different centers, but in different magnitude. For example, in center 1, A is better than B by 20%. In center 2, A is better than B by 10%. But at least in both centers, A is better than B. So this is also still called interaction, but this basically, the magnitudes are different, but the same direction. This is less problematic to you, but at least it's consistent. And again, you still have to investigate. We don't expect, if it's 20% difference between A and B, to be consistent 20% on center 1, 2, 3, 4. It's going to be maybe 16%, 20%, 22% across this. But you shouldn't see big differences. Whether it's reversed or not reversed, you shouldn't see big differences. And that's the main problem. I think yesterday, one of the studies that Dr. Fleihan talked about, there was in one country a different result in South America. She was talking about something. But they had to come up with what's the reason for that. Otherwise, you have to ignore all that center, data from that center, because sometimes it could be a conduct issue. Sometimes somebody is not following the protocol correctly. Or sometimes it's a coding issue. Somebody coded A instead of B and B instead of A. So it is a headache. And that's why you need to have a good quality control so that the results that you obtain from different centers make sense. They are all consistent. And if they are not consistent, you need actually to find the answer why. Okay? One thing also I want to mention, in one study we were doing actually we were doing a study in Qatar, Lebanon, Saudi Arabia, UAE, and Jordan. This is a study on rheumatoid arthritis. We're basically looking at genetics of rheumatoid arthritis. So we're recruiting patients from all these study centers. We had a problem because we were the central laboratory for all the blood. Actually, the blood comes to Cornell, Qatar, and then the blood goes actually to America for analysis, for genetics. Now, each country has its own rules about actually exporting the blood. And sometimes the blood will sit there for like 3-4 days. And you know, if it's not well kept, there's a problem with it. So each country we had, first of all, you get with the multi-center studies, you're dealing with multi-center IRBs. Have anybody dealt with an IRB here? Have any one of you dealt with IRBs? It's a headache. Sometimes it takes 2-3 months to get approval from IRB. And then sometimes you want to amend something, it takes another 2-3 months to amend something. Imagine doing it in 5 countries, in 5 institutions. Some of them were quick, because if you go through the Ministry of Health, if the Ministry of Health says yes, everything goes. Because usually the university is under the ministry. In some countries, it's the ministry is the one that actually making things difficult. Oh, you're gonna take blood of, let's say, Lebanese out to Qatar? No, we cannot. It's like, you go into details that are on a day-to-day basis are very complicated to manage, especially if there's blood and things like this, and involving DHL and everything. So basically, you need to think about this. But in a multi-center study, I put here a remark. It says the number of patients recruited from each center should be at least equal to the number of centers. So if I have, let's say, 20 centers, I would not recruit 1 patient from 20 centers. It does not make any sense in practice for cost effectiveness. Okay, and from statistics point of view, also you need the number of patients per center to be large, to be able to do analysis also per center. And sometimes the pharma companies, when they do these multi-center, they pick 1 patient from Lebanon, 1 patient. This is only for diversity. It's not really a multi-center study, okay? But they get a collaborator here, they get 2 patients from here. That's not really what we mean by multi-center study, the real ones. All right. Now we need a central laboratory for assessment of this. And this is because you want quality control in these labs. Now what you can do is you can actually send all the blood or the works to 1 place, or if you want to do x-rays, you want to do MRIs to 1 place, or you have to find accredited labs in each country that you trust. Most people prefer to bring all the specimens to 1 place and do it there. I mean, if I do my cholesterol level today in 3 labs here in Hamra, we'll get 3 results in the same day within half an hour. Okay, so that's why you want to have that quality control. And of course, standardization of procedure in all sites. This is the SOPs I was talking about. All the procedures has to be standardized and everybody has to be followed. And usually you have to monitor that. So it's more complicated in a sense. There's a lot of management that has to go through that to be able to make it work and make it work properly. But we are being able to do that now for a long time. And with all the things I talked to you about, the study in Qatar about rheumatoid arthritis went through, we had like 1.5 years to start with IRBs and things like this, and to finalize the issues of transforming blood and things like this. But it worked. We start publishing now articles from it. We have the specimens. We're doing more tests and things like this. So really, it pays off later on, okay? And really think big when you're writing these protocols. So for example, when you are getting blood, if you are storing blood, put in the consent that you might use this blood later on for another thing, because that's something that you can use. So capitalize on doing this. Some people go overboard in things. For example, if I'm doing a survey, they have like a 10-page survey and people don't respond. I mean, capitalize to a certain extent to the disease that you're working for. I'm working about rheumatoid arthritis. I'm not going to test them for any other genetic disorders for now. But just these things you need to think about when you're doing this. So the first thing we talked about is single site versus multiple site. The second classification I'm going to talk about is what is superiority versus non-inferiority trials. Okay, so superiority trials, again, very simple. The aim is to prove that the new drug is better, superior, or have bigger efficacy than a placebo or the current treatment. Okay, non-inferiority or equivalence trials is the aim is to prove that the new drug is similar or not worse than the current treatment. Of course, when we prove that it's not worse or similar, we have more, there's other advantages, which could be less toxicity, easier administration route, better quality of life, shorter duration of therapy, cheaper or minimally invasive techniques. So it has to have something, you have to sell it at the end, so you have to have something. Most of the generic drugs, for example, they prove themselves as non-inferiority drugs, and basically they're cheaper, okay? And that's why they're. Now, when you do non-inferiority trials, you have different statistical methods to be considered than the traditional ones used for superiority. Mainly, you're going to start using one-sided tests and one-sided confidence intervals in non-inferiority instead of what we do, a two-sided test now, the p-values and things like this. But we will go through this maybe one time later on when we talk about analysis. Now, the types of comparison in terms of your H1, okay, your hypothesis, in superiority trials, the aim is to prove that the difference between the two drugs is significantly different from zero. So basically, here I show you that delta of A minus B is different from zero. That's for a superiority trial. For example, if the whole interval, the confidence interval does not contain zero, is above zero, or all of it is below zero, you can also conclude that there is a significant difference, or you use the p-value. But here I'm going to use a confidence intervals more. So if you're deciding using a confidence interval, you need the whole interval to be above zero to say drug A is better than B, because A minus B is positive, or the whole interval to be less than zero, you then say A is lower than B, because it's negative. Now, equivalence trials is aimed to prove that the two drugs are equivalent, not equal. Be careful, you can never prove two things are equal in statistics. Actually, there's nothing is equal. There's no two things are equal. Even if you take the population, because there's always decimals at the end. Okay? So the aim to prove that they are equivalent, and this means that the difference between the two groups is lower than a clinically unimportant value delta. Okay? So basically I'm saying A minus B is between minus delta and plus delta. So the difference can fluctuate. So A could be better than B by a delta, or B is better than A by a delta. So, and that delta to me is clinically not important. That's them. And this is called we call it the non-inferiority or the equivalence threshold. Okay? And the question is, how do you decide on delta? Is delta 2%? Is delta 3%? And so on. And here, how you decide? Significance if the CI is all inside minus delta and plus delta. So if I compute A minus B, the whole interval, A minus B, and I do 95% confidence interval for A minus B, I want to know that A minus B, all of it is between minus sigma and plus sigma, or minus delta and plus delta. Okay? So that's basically how you prove it. Now, non-inferiority is aimed to prove that A is not inferior to B, and in such case is we talk that the delta of A minus B is less than, the difference between A minus B is less than a specific non-inferiority number. So I would say A minus B is less than 5%, but not B minus A, only one side. So I know A could be as good or slightly inferior. In the equivalence, it could be A is better than B by 5%, or B is better than A by 5%. No, in non-inferiority, I know that I might not reach B, but I'm saying, all right, if I'm still less than B by 5%, that's fine. So it's a one-sided thing, okay? And usually here, again, this cutoff that we put for ourselves, or the non-inferiority limit, is also subjective. And this is what people have to worry about. And based on this non-inferiority, the sample size is also computed, by the way. So if you decide you want to prove that A A is non-inferior to B by 3% or 4% or 5%, that affects your sample size computation for that kind of study. Okay? And so for the last one here, we usually use one-sided test because you're assuming that A cannot be better than B. Okay? So you use one-sided confidence intervals, and you want the whole interval to be below that threshold. So if I look at A minus B and all of it is less than 5%, then I say A is non-inferior than B. Okay. Any other question about this? Now, the next is, I'm going to talk just few slides on the types of trial. Okay? Yesterday, Dr. Fleihan also talks about these. There's dose response trials. So Moore in 1995, he said the difference between a drug and a poison is really the dose. Okay? So dose So dose response relationship on both efficacy and safety should be evaluated. And the objective of those dose response trials is to do confirmation of efficacy, dose response curve estimation, starting dose estimation, optimal stages of individual dose adjustment, and the maximum dose estimation. So this will help you in the future also look at make this drug better in terms of all these kind of estimations. You can have combination trials with like factorial designs. Effect of combining two active drugs together. Each drug acts through a different mechanism. We're going to talk about this. You don't, when you do a factorial design, when you try to test two drugs at the same time, for example, I would not give a person two types of diet at the same time, or two ACE inhibitors at the same time. You have to have, the drugs has to act differently on the disease. You worry about, in these kind of trials, in the combination trials, you worry about interaction between these, and it could lead to severe side effects. Okay, and again, the objective is to determine sometimes the range of therapeutic dosing of those, order of administration, duration of each drug, and it's more a complex process. We'll talk about really a simple, what we call a 2x2 factorial design, where I have two drugs. I'm testing two drugs, combination of two drugs versus each drug separately, whether the two drugs is better than each single drug. All right. So we talked about multi-center single site. We talked about superiority versus non-inferiority, a little bit about the different types of studies. Now I'm going to talk about blinding and randomization. These are the main issues. There's three, actually. I would add one point here on slide 10. It says key points in the design of a clinical trial. The first key point is blinding, if you can blind people. The second point, which is the most important point, is randomization. This is the most important point. And the third point we'll add here is, of course, the sample size, the power of the study. This is in the design part. So the design part, when I'm going to look at the design part, besides looking at the research question itself and looking at how important the study and whether the outcome is important or not, or appropriate outcome from a design statistical point of view, I would look blinding, randomization, and sample size and power. Now, these, especially randomization, yesterday Dr. Fleihan talked about internal validity of the study and the external validity of study. Okay? The internal validity of a study, for example, suppose you're comparing A versus B. I want to prove that whatever comparison I got from A minus B is an accurate difference. When I compare A minus B and I get a p-value, I want to prove that this actually design, this result is accurate. That's internal validity. External validity is basically generalizability of the results to the outside. That's external validity of the study. And that's basically what type of patient I include. If I only include severe types of patients, high-risk patients, then I can only generalize it to high-risk patients. Okay? If I include low-risk patients, for example, the study on hormone therapy replacement, 65 years old. Although it doesn't work for 55, but you can say at 65, if I treat them at 65, this is the results. Okay? So that's basically the external validity. Basically, I call it generalizability of the results. And internal validity is how accurate are your results in the study itself, how accurate. That's internal validity. So blinding and randomization are very important for the internal validity and the sample size, of course. If you have underpowered study, you might get false results. What happens if you have an underpowered study. In other words, you have a sample size that's smaller than what you need. What do you think will happen?
Maybe the detection point is beyond it.
So the confidence interval gets wider. What does it mean in terms of significance? Usually p-values go up. Okay? So basically, you might see the difference, A is better than B by 20%, but your p-value is still above 5%. So it's not significant result. So that's inaccurate. So that's internal validity of the study. Okay? Inaccuracy because of sample size. Randomization, we're going to talk about it. If randomization does not work, again, that affects internal validity. So let me talk a little bit about those, and then I promise you I'll stop. I'll stop just, and then we'll pick it up. I mean, we went only 10 slides, so you don't need to panic. So blinding or masking, this is very simple. Blinding is basically withholding the information about the treatment allocation from patient, treatment physician, investigator, or biostatistician. The goal is to reduce bias due to the subjectivity in reporting by patient. So if I'm a patient and I know what I'm getting, okay, especially if the outcomes are soft outcomes, okay, they're not blood pressures or soft outcomes, then I might report that I'm doing better because I'm only taking the good one. Or the totally opposite. Some people like their drugs. They don't want to change. When you give them something different, they tell you, I start having headaches. They start imagining things. So blinding protects you from that, okay? Even if the outcome is not really a soft outcome, they might start doing, if you give them a new drug, they might start exercising, okay? And that actually, you don't know if it's the exercise or the new drug. So really, reporting by the patient or what the patient does, if they know or don't know, might actually be biased, and we're not saying it's gonna be biased, might be biased by if the patient knows what they're getting or not. Evaluation by the physician. Again, there's conflict of interest. Some physician might like the new drugs. They might see it's cheaper, and I think my patient should get the cheaper one. They might say it is better or something, or they read an article, or the pharma companies is actually paying them. I don't know. But again, the physician might actually be biased by knowing which one is getting what. And finally, the statistician. As a statistician, if I have invested money in drug A, I might actually, I don't play with the data, but instead of using t-test, I use a non-parametric test because it gave me a significant result. So I try 3 things. The one that gave me a significant result, I reported, and then I justify it. And there could be bias. If you want to be ethical, really, you don't go over all these. But we don't live in an ideal world, all right? So sometimes it's not feasible even to do that. I mean, for ethical reasons or due to the nature of the intervention. For example, a lot of the oncology trials are not blinded. I mean, how are you going to blind a person with cancer? They're not blinded, okay? If you're comparing a drug versus surgery, you cannot blind people. The drug is a drug, the surgery is surgery, so you cannot blind, okay? So there is the type of the drug, or for ethical reasons, you cannot blind people. Also, it can be breached. Yeah, people can guess what they're getting because they are used to getting a certain taste, and now they're not getting the taste, or they start getting like side effects they never experienced before. So they might guess what they're getting, okay? So that can be breached due to the severe side effects or taste of the medication. And hopefully what we do, pills, usually we ask the same company to do the same pills, but if you're doing pills, yeah, comparing 2 different drugs, you cannot tell them to do that. And of course, in very extreme situations, such as occurrence of extreme side effects, unblinding should be necessary to be able to treat the patients. There is a new concept in research where they ask physicians and they ask actually patients. The physician can guess from the outcome of their patient or the reaction, and the patient can guess. So usually we ask them, in some cases we try to ask the patients, do you guess what you got after blinding and after the study. If 90% or 80 or 90% guessed, we think that's not unblinded. You can treat it as an unblinded study because you expect 50% because that's a guess. 50-50, you have a chance of guessing it 50-50, but if you get a rate that's 80 or 90%, it's not blinded anymore, okay? People are knowing what they're getting from the beginning. Okay. Now, these are the classification you find in the literature. Open label, basically, it's not blinding. Patient and physician know which treatment the patient is getting, which is fine. We do a lot of open label studies. Single blinded, usually the patient does not know what the drug he or she is taking. Double blind is the gold standard, usually, is when the patient and the physician don't know. And to be honest, triple blind, I never seen any person write triple blind. But triple blind is when actually the analyst or even sometimes the sponsor don't know who's getting what. So for example, the sponsor will come to AUB and say, I'm going to do this. So the AUB people will actually do the blinding and everything. The sponsor does not know. They know A and versus B. Okay? And then at the end, they unblind. Although there should be somebody who's unblind to know what's A and B. Otherwise, we're problematic. We finish the study and we don't know. I'll tell you a couple of things. What we did a study here at AUB where actually the pharmacist was the person who knows. And the pharmacist will prepare the drugs and send them versus A and B. But we don't know. Especially the people recruiting the patient or the people actually evaluating the patient, they don't know what A and B. So that's it. Sometimes you have to be innovative. Sometimes we were giving actually an intravenous drug that has a color. I mean, I don't remember the color. And we couldn't do a saline with exactly the same color. So we did two things to protect ourselves because we want to blind. So we wrapped the syringe with like black tape so the person cannot know. And the nurse who was actually inserting the syringe was doing it under a blanket where the physician does not see her if a drop falls and so on. Imagine what we did all of that to unblind the physician. Okay, so you have to come up with things to do, and this was written in the protocol because the IRB came. It's like, how are you going to unblind them? How can you blind people because these actually it has color. This one has color. You cannot replicate this, and then that's what we did, and it worked. I mean, at least to our knowledge that this was working. All right, this is a cartoon of a double blinded where you can see both the physician and a patient has blindfolds, and the physician is giving the patient actually the drug. How to blind? Pharmacists, companies can prepare the drugs which should be identical in size, texture, packaging, taste, and just label them as A and B. The physician will receive a randomization sequence. We will see later how we can generate this, such as A, B, and so on. So patient number 1, A, and so on. So for the first patient, he receives drug A, the second receives drug A, the third drug B, according to this sequence. Note also that the biostatistician will only get codes A and B for the drugs and will not know what A and B. That's why I was saying earlier, triple blinding on slide number 12 is automatic. As a statistician, I only get A and B. I don't get the names. Well, saying that, I get the names sometimes. Okay? I get the names of the patients sometimes. I get names of cancer patients sometimes. And there is, as much as we train people sometimes, people take you for granted. I know Ziad, he's a nice guy. I don't have time to take off the names. Like maybe my aunt was in this or somebody I know. There is some issues that goes around the statistician sees like, and then I email them directly. I say, please take this out. Please take the names out. Keep the ID, the patient ID in. I don't need to see the names. Because if these are patients from Lebanon, I will definitely look at the names. Curiosity. And I see somebody from Mahfoud, and it's like, look, okay, where from where? So this is human being. So the physician should not send me the data actually like that. They should not even store it like that to be starting with. Anyway, but basically we are blinded usually as codes, A and B. We get a lot of codes. I work with Dr. Flyhan a lot. She sends me codes, A and B. So this is code A and B. I don't know. To me, it doesn't matter because I'm not an MD, and if even I get something, I don't know what it means sometimes. All right? I'm a statistician who's curious because I go to Google when she says vitamin D 1OH25. I go and say, what is that? I mean, I want to know what I'm analyzing. So some people analyze it without thinking about these, but over the years I learned a lot of medical things. But anyway, the first time, for example, I did something on diabetes, HbA1c. What's HbA1c? I have no idea. 7%. Like, why 7%? So I went, did my research, and just to understand. I didn't need to do that. But if you are analyzing something, please understand what you're analyzing. We are not machines, yani. But this is something that you need to do. Okay, at the end of the study, the pharmacist or the principal investigator who is not involved in the recruitment, this is very important, who is not involved in the recruitment of patients will declare what is A and what is B. So after you do all of this, the pharmacist send this, at the end they do. The final slide, I'm going to go a couple of slides, is another type of blinding, and then we'll do randomization next time. It's called probe, prospective randomized open label blinded endpoint, probe. P is for prospective, R is for randomized, O is for open label, B is for blinded endpoint. It's an open label where both the patient and the physician know the treatment allocation, but they are blinded to the endpoint of interest. Okay? Now, there is some kind of an ethical issue here, because in the informed consent, you should tell the patient what's the endpoints usually. And some people say we're going to look for heart disease, but they're looking for a specific something in heart disease. Okay? It could be mortality or it could be very specific. The endpoints are assessed by an independent committee who's blinded to the treatment. So the physician prepared the dossier, and then basically this committee sits and looks at that file and decide whether the outcome, for example, if this is a death related to the drug or not, or what is the outcome. Okay, so they are blinded to the allocation. When they get the file of the patient, they don't see the medication that was given. And I'll give, yes.
How can we make sure that the physician reports the outcome?
The physician who's reporting the outcome is not in the committee. So the physician knows the drug. He reports all the outcomes. The committee, but he doesn't know which outcome the committee is going to pick. Okay, so this is the idea. Now, and these outcomes, I mean, you cannot really play with them. I'll give you, this is an example. This is an article. So it says, reduced cardiovascular morbidity and mortality in hypertensive diabetic patients on first-line therapy with an ACE inhibitor compared with a directed beta blocker-based treatment regime. So I highlighted few things for you. This is called the CAPP, was conducted at 536 health centers in Sweden and Finland, using probe, prospective randomized open label study designs. And then they say the primary endpoint was the combination of fatal and non-fatal myocardial infarctions and stroke, as well as other cardiovascular deaths. Events were evaluated by an independent and blinded endpoint committee before being accepted. Okay? And then we'll talk later on what's intent to treat analysis. So this is, we haven't used it in the region. I haven't used it myself. I've done a lot of clinical trials in the region. And even in the literature, you don't find two things. But this is one way to keep in mind. Yani sometimes we come up with creative ways in order to get even the outcome. The outcome is blinded, although everything is unblinded. But if we can blind the outcome, or the person who's assessing the outcome. So for example, you can send a physician to evaluate a patient and telling the patient, please don't tell him what the drug you took. Okay, that's blinded outcome. Okay, but this is some kind of this kind. All right, I'm gonna stop here. Okay, so I'll stop here. So just we went through the first 16 slides. I'll actually post this. Next time we'll meet will be actually in October 6, 7. So it's far from now. But what you expect from me is I'll send you next week homework number 1. Okay? Homework number 1, and I'll give you plenty of time to look at it. It usually takes 1 or 2 hours to do the homework. And you have the slides in front of you. These are simple things. It's just to give you practical examples of what we learned in these phase 1 and phase 2. Okay? And some multiple choice questions just to look at perspective. Again, and this, you can actually work together if you want. If you want to ask me, by the way, I have an email at Cornell. Please send. I have 2 emails, one at AUB, one at Cornell. Please send me to the Cornell one, because that one I check all the time on my phone. You can send me a WhatsApp on my Qatari number. I think it's on the syllabus, if I'm not mistaken. If not, let me write it here. You can send me a WhatsApp. But please, Anna, I don't know your names all right now, but let me know that you are from the EPHD. So 974 plus 974 66887504. So 974 66887504. This is my Qatari number. Just send me a WhatsApp if you need any questions, or we can Skype if you want to. And if you want to discuss something, that's no problem. So anyway, you want to contact me, that's fine. So just expect from me a homework. If there is any reading I would like to send you before next time, then I don't expect to send you anything. Now there is a small series that was in, I think, JAMA or Lancet, like a one-pager on sample size, a one-pager on randomization, a one-pager on this. These I actually will include on Moodle for you. These are articles, but 1 or 2 page, I think, on simple topics that we will discuss next time. It will be nice if you can read them before, but you can read them after next time. That's no, if you have other things to do. But these are good concept papers, okay? Just 1 or 2 pages each one. Any questions? All right, so enjoy the rest of your weekend, and we'll see you in about 3 weeks.